Mary's room. Mary is a scientist who lives in a black and white room. Everything she sees, her books, her screens, even her food, is grayscale. She's never seen a single color. But Mary specializes in color vision. She knows every scientific fact about how humans perceive color. She understands the physics of light, the biology of the retina, the neural pathways in the brain. If you asked her what happens when someone sees red, she could explain it in complete detail, down to the molecule. But then one day, Mary leaves the room. She sees red for the first time. The question is, does she learn something new? If she does, then there's a kind of knowledge that goes beyond physical facts. Something you can't learn from studying diagrams or reading scientific papers. That something is called qualia, the raw feel of experience, what it's like to see red, to feel pain, to taste cinnamon. This is the core of Frank Jackson's famous thought experiment from 1982. It challenges physicalism, the belief that everything, including the mind, can be explained in physical terms. If Mary knew all the physical facts but still learned something new by seeing red, then physicalism is incomplete. That would mean subjective experience, consciousness itself, can't be reduced to biology or physics. It suggests there's a mental world that can't be captured by science. But critics of the argument push back. Some say Mary didn't learn a new fact. She gained a new skill, a different way of accessing the same information. Like someone who knows how bikes work, then finally learns to ride one. Others argue the thought experiment relies on an unrealistic assumption that we can truly know all the physical facts in the first place. Still, the challenge remains. Can you fully understand an experience without ever having it? If not, then no matter how advanced our science becomes, something will always be missing, something deeply human. Not everything can be measured. Some things must be felt. This is Mary's room. And it asks a simple but unsettling question: can the mind be explained entirely in terms of matter? Or is there something about being human that escapes even the most complete scientific theory? What you've just seen is one thought experiment, and already it challenges the limits of knowledge itself. This is what thought experiments do. They don't give answers, they reveal how deep the questions really go. Across centuries, philosophers have used them to probe the hardest problems we face, from identity and morality to consciousness to the nature of reality. This video is only the beginning. What follows are just the entry points, the foundational challenges. There are levels beyond this, and if you're ready to explore those, subscribe and continue the journey. Galileo's falling bodies. Picture a tower, a tall one, stone steps spiraling up. At the top, Galileo stands with two objects, a heavy cannonball and a small lead sphere. According to Aristotle and centuries of belief, the heavy object should fall faster. That's what people knew. Heavier things fall quicker. It made sense. It felt right. But when Galileo dropped both objects together, they hit the ground at the same time, nearly identical. And with that one moment, physics changed forever. This is the story behind Galileo's falling bodies, a thought experiment that was probably also done in real life, and it destroyed the ancient idea that motion was based on weight. Galileo proposed something radical for the time. In a vacuum without air resistance, all objects fall at the same rate, regardless of mass, whether it's a feather or a hammer, a marble or a boulder. If nothing gets in the way, they fall the same. Why? Because gravity acts equally on all objects. It accelerates everything at the same rate, about 9.8 meters per second squared on Earth. This was a fundamental shift. It meant that nature didn't play favorites, and that intuition, what feels true, isn't always right. Galileo didn't stop at dropping things. He used ramps and inclined planes to slow motion down, to study how speed builds, and he introduced a new way of thinking. Measure, observe, test. Don't trust what seems obvious. Test. Before Galileo, physics was mostly philosophy. People thought more than they experimented, but Galileo mixed both and laid the groundwork for Newton, for Einstein, for the entire scientific method. But the story doesn't end with cannonballs, because this principle, equal acceleration, isn't just about falling. It connects to how we understand inertia, momentum, force. It leads directly to Newton's laws of motion. And centuries later, it became a key piece of Einstein's theory of general relativity. Einstein called it the equivalence principle. That being in free fall is indistinguishable from floating in space. That gravity isn't a force pulling you down, it's the curve of space and time bending your path. And all of that starts here. With two objects and a tower. Galileo's Falling Bodies Revisited isn't just a lesson in physics, it's a reminder that the world often contradicts our expectations. That what seems right can be wrong. That science moves not by defending what we believe, but by testing what we think we know. The Gettier Problem. For a long time, philosophers thought they had a solid answer to one of the most basic questions in philosophy. What is knowledge? The traditional view went like this. To know something, three things must be true. You have to believe it. It must actually be true. You must have a good reason for believing it. That sounds right. If you believe something, and it's true, and you have a logical reason to believe it, you know it, that's called the JTB model, justified true belief. But in 1963, a philosopher named Edmund Gettier published a 2-page paper that changed everything. In it, he showed that you can have all three parts, belief, truth, and justification, and still not really know something. Let's look at an example. Imagine you're in an office. You look at a clock on the wall. It says 2:30. You believe it's 2:30. The clock is usually reliable. You have no reason to doubt it, and it is actually 2:30. So you have a justified true belief. But here's the twist. The clock broke 12 hours ago. It's been stuck at 2:30 ever since. You just happened to look at it at exactly the right moment. Your belief is true. You're justified in believing it. But it was an accident. You got lucky. And most people would agree, that's not really knowledge. You were right, but for the wrong reasons. That's a Gettier case. It's a situation where all the traditional boxes are checked, but something still feels off. Your belief was correct, but it wasn't solid. It wasn't really connected to the truth in the right way. Gettier gave a few examples like this, and philosophers started finding more. The core idea is always the same. A lucky guess isn't knowledge, even if it turns out to be right. This broke the old definition of knowledge. Ever since, people have tried to fix it. Some added a fourth condition, no false steps in the reasoning. Others said knowledge has to be safe. It has to hold up in nearby possible situations. Some even said we should throw out the whole idea of defining knowledge and just accept that it's a fuzzy, messy concept. But no one has come up with a definition as simple and clear as the one Gettier took down. That's why the Gettier problem still matters. It shows that even the things we're most confident about, like knowing what it means to know, can fall apart under pressure. And it reminds us that sometimes being right isn't the same as understanding. The inverted spectrum. Think about the color red. Imagine a stop sign, a fire truck, a ripe strawberry. You know what red looks like, right? But here's the question. How do you know that your red is the same as my red? What if what you see is red, I see as what you would call green, but we've both learned to call it red because that's how we were taught. The stop sign still means stop. The strawberry still looks ripe. We both behave the same. But inside our minds, our experiences of color might be completely different. That's the inverted spectrum thought experiment. It asks, could two people see the world in different ways while acting exactly the same? And if so, would we ever know? The idea comes from philosophers like John Locke and later was sharpened by modern philosophers of mind. It's not about being colorblind. It's not about your eyes being damaged. It's about whether subjective experience, what philosophers call qualia, can ever be compared. Suppose you and I have perfectly healthy brains. We both pass every color test. We agree that grass is green, the sky is blue, bananas are yellow. But what if, deep down, the way those colors appear to us is totally different, flipped, inverted, rotated, like we're each living in our own color filter, we'd never notice. Because our behavior and language would still match. If I say, that's a bright red apple, and you say, yes, that's red, we seem to agree. But we could be talking about two entirely different visual experiences, mapped to the same word. There's no way to look into someone else's mind and compare what they see. That's the point. The inverted spectrum exposes a hidden gap, the gap between how we act and how we experience things. Philosophers use this thought experiment to question functionalism, the idea that mental states are defined by what they do, not how they feel. According to functionalism, if your mind behaves the same way as mine, if your inputs and outputs match mine, then our experiences must be the same. But the inverted spectrum says, maybe not. Maybe behavior alone isn't enough to explain consciousness, because what we're really interested in isn't what we say, but what it feels like. And that feeling, subjective experience, is private, entirely locked inside the mind. Some people think this proves there's more to the mind than just physical processes, that consciousness has a mysterious inner layer that science can't fully capture. Others argue it's just a trick of language, an illusion caused by how hard it is to describe inner experiences. But whether or not the inversion is real, the thought experiment still matters. Because it reminds us, you can never fully know what it's like to be someone else. You can guess, you can empathize, you can ask questions, but you'll never see my red, and I'll never see yours. That's not just about color, it's about the whole of consciousness. Pain, joy, fear, hunger, love, they might be described with the same words, but they live in private worlds. And the inverted spectrum is a quiet reminder of how separate those worlds really are. The lazy argument. If something is meant to happen, it will happen. If it's not meant to happen, no matter what you do, it won't. So why bother trying? That's the lazy argument, a classic form of fatalism. It shows up in different forms across cultures and philosophies. But in ancient Greece, the Stoics took it seriously enough to argue with. The logic goes like this. Suppose it's fated that you'll recover from an illness. Then you'll recover whether or not you see a doctor, and if it's fated that you won't recover, then seeing a doctor won't help. So, either way, why bother? If fate rules the future, then your actions don't change anything. That's the trap, because it sounds logical. It feels like a shortcut to peace. Let go of control, stop worrying, just accept what comes. But it also sounds like an excuse to do nothing, to wait for life to happen to you instead of acting on it. The Stoics, especially the philosopher Chrysippus, rejected this idea. They believed in fate, yes. But they said that fate doesn't mean events happen no matter what. It means things happen in a certain way, connected through causes. So if it's fated that you'll recover, it's also fated that you'll go to the doctor. Your action is part of the chain. Just like it might be fated that a crop grows, but only if the farmer plants it. In other words, your choices are still necessary, not because they break fate, but because they belong to it. The lazy argument tries to separate fate and action. The Stoics said, you can't. The future isn't a fixed destination waiting regardless of the path. The path is part of what makes the destination happen. That idea still matters today. People often fall into modern versions of the lazy argument. If I'm meant to succeed, I will. If it's meant to be, it'll happen. But those ideas can quietly drain effort, ambition, or responsibility. They make us wait for the world to decide instead of acting with intention. The Stoics weren't telling people to control everything. In fact, they taught the opposite. Control is limited. You can't decide what happens to you, but you can decide how you respond. And that response matters. It becomes part of the outcome. So yes, some things are outside your power. But what you do with the part that is in your hands, that might be the only freedom you ever really get. The puzzle of the self-torturer. Imagine a machine. It's hooked up to your nervous system. Every time you press a button, it increases your pain sensitivity just slightly, barely noticeable. Button 0, no pain at all. Button 1, a faint tingle. Button 2, still manageable. And so on. The twist? Each time you press the button, you get $10,000. Press it once, make 10 grand. Press it 100 times, make $1 million. And you can stop at any time. Here's the catch. At some point, the pain becomes intolerable. But when? That's the puzzle. This is the self-torturer, a thought experiment introduced by philosopher Warren Quinn. And it's not really about money or pain. It's about gradual change, and how our reasoning can fail when change is too small to notice. Let's say you're at level Bristol point. Level 1 is barely worse, totally worth $10,000. Same with level 2. Still worth it. Level 3? Again, the difference is tiny. Why stop now? But keep going. 20, 50, 70. Eventually, you're in agony. And you ask, how did I end up here? The answer? One logical step at a time. At each point, moving forward seemed like the right call, but the accumulation led to a place you never would have chosen all at once. That's what makes it disturbing. Each step is rational, but the whole path leads to something irrational. This is a version of what philosophers call a Trolley problem, from the Greek word for heap. The same logic that makes it hard to say when a pile becomes a heap makes it hard to say when tolerable pain becomes intolerable, or when a few bad decisions become a ruined life, or when a few compromises become a total sellout. The self-torturer applies this to practical reasoning, because in real life, we make decisions incrementally. One more hour at work, one more compromise, one more push past our limits. None of them feel like much. Until they do. And once you're far down the path, it's hard to undo. You can't unpress the buttons. You can only ask, where should I have stopped? Some people say the solution is to set a hard limit in advance. Maybe press the button 10 times and walk away. But that's hard to stick to, because each time you're tempted by the next step. $10,000, just a little more pain. You don't feel the line until you've crossed it. Others say the answer is to accept trade-offs as real, even if the differences seem small. That just one more can matter, even when it feels harmless. That you have to think about where the path leads, not just where you are. The puzzle of the self-torturer isn't about a fictional machine. It's about life. About habits, ambition, burnout, addiction. About how we tell ourselves, it's fine, until it's not. And how even the smartest minds can reason themselves into pain. Galileo's ship. Imagine you're in the cabin of a large ship. There are no windows, no portholes. You can't see the ocean. Inside the room, things feel completely normal. A glass of water sits still on a table. A ball bounces perfectly up and down. A butterfly hovers in the air. You could walk around, play cards, eat lunch. Everything works the way it does on land. Now here's the twist. The ship is moving, not just slowly drifting, it's sailing at a constant speed across the sea. And you have no idea. That's Galileo's ship, a thought experiment from the early 1600s. It was Galileo Galilei's way of showing something revolutionary. If you're moving smoothly, in a straight line, you can't feel the motion from inside. And that idea changed everything. Before Galileo, people thought the Earth couldn't possibly be moving. After all, we don't feel it. If the Earth were flying through space, wouldn't we notice? Wouldn't birds fall behind, or water spill out of cups, or the air get ripped away? But Galileo said, no. If the Earth is moving at a constant speed, and everything on it is moving with it, then from inside you feel nothing. Just like being inside that windowless ship. Your body, your breath, the glass of water, the butterfly, they're all moving together. So from your point of view, it's like you're not moving at all. That's the power of relative motion. Motion only makes sense when compared to something else. If you're sitting on a plane flying smoothly at 500 miles per hour, you can still pour a drink or play chess because everything around you is moving with you. You only feel motion when there's a change, speeding up, slowing down, turning, but constant motion. That's invisible from the inside. This was a radical idea because it meant there's no single universal stillness. There's no cosmic scoreboard saying who's really moving and who's not. You could be standing still on the deck of a ship or moving at 1,000 miles per hour on the spinning Earth, and without looking outside, you wouldn't know the difference. That became the foundation for modern physics. Hundreds of years later, Einstein took this idea even further. He showed that motion doesn't just affect how we see objects. It affects space and time themselves. Time moves slower for someone traveling at high speeds. Distances shrink. Mass increases. All of that starts with Galileo's simple question, what can you feel from inside a ship? And the answer is, not much, because motion is relative. It depends on your point of view. Maxwell's demon. In the 1800s, scientists discovered a strange rule about the universe. Left on its own, everything tends toward disorder. Ice melts. Rooms get messy. Batteries run down. This is called the second law of thermodynamics. It says that entropy disorder always increases over time in a closed system. Heat spreads out. Energy becomes less useful. It's not just a physical rule. It's a kind of cosmic direction. Things break down, not build up. But in 1867, physicist James Clerk Maxwell asked, what if we could cheat that rule? He imagined a box filled with gas. The box is divided in two halves. A tiny door connects the sides, and at that door there's a creature, a little demon. The demon isn't evil. It's just clever. Its job is to observe the gas molecules bouncing around and open the door at just the right moments. If a fast-moving molecule comes toward the door, the demon lets it through to the right side. If a slow one approaches, the demon sends it to the left. Over time, the fast molecules collect on one side and the slow ones on the other. That means one side gets hotter and the other gets cooler. In other words, the demon just reversed entropy. It created order from chaos without using any energy at all. According to the second law, that shouldn't be possible. So what gives Seth? This is the puzzle known as Maxwell's demon. It seems to break the laws of thermodynamics just by being smart. For decades, no one had a solid answer. But eventually, physicists started to look at information as the key. The demon needs to measure each molecule and remember its speed. That takes memory, which takes physical space. And at some point, to keep working, the demon has to erase old data. But erasing information creates heat. That's the twist. The act of deleting information costs energy, just like moving a piston or burning fuel. So in the end, the demon doesn't cheat the system. The entropy goes somewhere. It's just hidden in the cost of thinking. What started as a physics problem became something else entirely. A link between information and energy, between thinking and thermodynamics. And this idea isn't just theoretical. Today we build computers with bits that flip, store, and erase information, and every bit has an energy cost. Even in the smallest machines, the laws of physics and information are deeply connected. Maxwell's demon shows us that intelligence isn't free. That knowledge itself has a cost in the physical world. And that even the smartest system can't escape the rules of entropy. It just shifts the mess somewhere else. The experience machine. Imagine a machine that can give you any experience you want. You could live your dream life. You could become a famous musician, climb Everest, fall in love, win the Nobel Prize, all without ever failing, suffering, or feeling pain. The machine makes it feel 100% real. You won't know it's a simulation once you're inside. To you, it'll be your life. But once you plug in, you can't come back. So here's the question. Would you choose to plug in? This is the experience machine. A thought experiment from philosopher Robert Nozick in 1974. It's meant to test how we think about pleasure, reality, and what actually makes life meaningful. A lot of people think happiness is the goal of life. More pleasure, less pain. That idea is called hedonism. And Nozick wanted to challenge it. If all that matters is feeling good, then plugging into the machine should be the best possible life. No pain, no failure, no heartbreak, just joy, success, and comfort. But most people hesitate. Some say no. Why? Because something feels wrong about living in a perfect illusion, even if we don't know it's fake. We want our achievements to mean something. We want relationships with real people, not computer-generated ones. We want to do things, not just feel like we did. Nozick argued that this shows we care about more than pleasure. We care about being a certain kind of person, about living in contact with reality, even if that reality is hard. The experience machine makes us question what we really value. Is it better to live a perfect lie or a difficult truth? It also ties into modern issues. Think about virtual reality or social media filters that let people create ideal versions of themselves. Think about video games where players escape to fantasy lives. These aren't full-on experience machines, but they start to ask the same question: when does simulation become a replacement for reality? And if we prefer the fake version, what does that say about what we want from life? Some people argue that if the machine gives you the same emotions, the same joy, then why not choose it? If the brain can't tell the difference, does it matter? Others say it's a trap. If we lose contact with the real world, we lose our agency. We become passive. We stop growing. Because real meaning comes from struggle, choice, and effort, not just comfort. So would you plug in? If everything you wanted could be yours, but none of it was real, would that be enough? The Sleeping Beauty Problem. You volunteer for a strange experiment. On Sunday night, you're put to sleep. While you're unconscious, the researchers flip a fair coin. If the coin lands heads, they wake you up on Monday just once. If it lands tails, they wake you up on Monday and Tuesday, but each time they give you a drug that makes you forget the previous awakening. Either way, you don't know what day it is when you wake. You just open your eyes and hear, "Welcome back, Sleeping Beauty." And now they ask you a simple question. What is the probability that the coin landed heads? Your instinct might say, it's a fair coin, 50-50. But hold on, if the coin landed heads, you're only woken up once, on Monday. If it landed tails, you're woken up twice, once on Monday, once on Tuesday, and each time you wake up, you don't know whether it's Monday or Tuesday. From your point of view, waking up like this is twice as likely under tails than under heads. So should you say the chance of heads is only 1 in 3? This is the heart of the Sleeping Beauty problem. A simple setup, a single coin, 1 person, 2 days. But it sparks deep arguments about probability, evidence, and belief. There are 2 main camps. The Hafer view says the probability is still 50%. The coin is fair. You knew the setup before you went to sleep. Waking up gives you no new information. So the chance that it landed heads is still 1 in 2. The Thirder view says the probability is 1 in 3. Why, imagine repeating the experiment 1,000 times. About 500 times the coin lands heads. In those you're woken up once each. About 500 times the coin lands tails. In those you're woken up twice each. That's 1,000 wake-ups. So in total, there are 1,500 wake-ups. Only 500 of them are heads. So on any random waking, the chance you're in a heads world is 1 out of 3. Still with us? Good. Because here's where it gets philosophical. The problem isn't just about math. It's about how you update your beliefs when you're missing context, when you lose memory. When your point of view doesn't include the full picture. Some say this puzzle shows the limits of classical probability. Others say it proves we need to distinguish between events and observer moments. In one version, you're calculating how likely it is that the coin was heads. In the other, you're calculating how likely it is that you are in a particular waking moment. The difference is subtle, but it changes everything. And this isn't just a game. Similar reasoning shows up in science, in cosmology, even in debates about consciousness and simulation. When we try to guess how typical we are in the universe, or whether we're in a simulation, we're doing a version of Sleeping Beauty's puzzle. What should we believe, based on where we find ourselves, and what we're allowed to remember? There's no consensus. Philosophers still argue. Halfers hold their ground. Thirders make their case. And the rest of us just wake up confused, wondering what day it is, and whether we've already been here before. Newcomb's paradox. There's a game. You walk into a room and see two boxes. One is transparent. You can see it has $1,000 inside. The other is opaque. You can't see what's in it. A superintelligent being, call it the predictor, has already made a prediction about what you will do. If the predictor thinks you'll take both boxes, it left the opaque one empty. If it thinks you'll take only the opaque box, it put $1 million inside. So you have two options. Take both boxes and get $1,000 for sure, plus whatever's in the opaque box. Or take only the opaque box, hoping the predictor believed in you and left you the million. What do you choose? This is Newcomb's paradox. And no matter what you pick, you'll feel like you did it wrong. Let's break it down. Some people say, take both boxes. Why not? The predictor already made its decision. Either the million is there, or it isn't. You can't change the past. Might as well take the extra 1,000. That's called the dominance argument. More is better, but others say, wait a minute. The predictor has an incredible track record. It's been right 99.9% of the time. If it predicted you'd take both boxes, it left the million out. If it predicted you'd take only one, it rewarded you. So if you want the million, you should commit to taking just the opaque box. That's called the expected utility argument. It's not about what makes sense now, it's about what the best strategy is proven to be. And here's the tension. Do you act based on the current facts, or do you act as if your decision is somehow tied to the prediction? Even though the predictor made its choice before you entered the room, your action still seems connected to its guess. That's what makes this a paradox. It challenges the way we think about free will, prediction, and rational choice. If you believe in free will, you'll say, I choose what I want, and no prediction can bind me. But if the predictor really is that good, it seems like your free choice was already predicted with near-perfect accuracy. So are you making a decision, or are you following a path that was already expected? Some say this shows that free will is an illusion. Others say the problem reveals a gap in how we define rationality. Should you act based on logic in the moment, or based on patterns that are bigger than you? There's no clear answer. Philosophers and mathematicians still argue about which choice is more rational. And whichever you pick, you can always imagine that you could have done better. That's what makes it a paradox. The more you think about it, the less obvious your decision becomes. Russell's teapot. Imagine someone tells you there's a tiny teapot orbiting the sun. It's way out in space, between Earth and Mars. But it's too small to see with any telescope. No one's ever detected it, but it's definitely there. Can you prove them wrong? Probably not. But does that mean you should believe them? This is Russell's teapot, a thought experiment by philosopher Bertrand Russell in 1952. It's not really about teapots, it's about belief without evidence, and who carries the burden of proof. Russell's point was simple. Just because something can't be disproven doesn't mean it's reasonable to believe. If I claim that something exists, but give no evidence, you don't have to prove me wrong. I have to prove I'm right. That's what we mean by the burden of proof. The more extraordinary a claim is, the stronger the evidence needs to be. The teapot example is meant to sound silly on purpose. Because lots of claims, especially about the supernatural, the divine, or the unfalsifiable, work the same way. People sometimes say, well, you can't prove it doesn't exist. And Russell's reply is, that's not how belief works. If someone told you a ghost lives in their closet, or that there's an invisible dragon in their garage, or that unicorns exist on a planet we can't reach, you wouldn't take that seriously just because no one can disprove it. Lack of disproof is not proof. The teapot is a metaphor for beliefs that are protected from criticism because they're set up in a way that avoids evidence entirely. But Russell's point wasn't to mock belief. It was to defend rational skepticism. He was saying, if you want to believe in something, it's okay to ask why. Not to be rude, not to be arrogant. He sees, but because beliefs shape actions, they matter. And if we don't ask for reasons, we can end up believing anything. Some people misunderstood Russell's argument as saying, you should never believe in God, but that's not the claim. He wasn't trying to disprove religion. He was saying that the rules of belief should be consistent. We don't accept wild claims without evidence in science, medicine, or law. So why treat metaphysical claims differently? Why is it okay to demand evidence for a new medicine, but not for an invisible teapot in space? The power of the thought experiment is that it forces us to zoom out, to ask, what do I believe and why? How much evidence do I need before I say something is real? And when do I stop pretending that maybe is the same as probably? Russell's teapot isn't just about religion or science. It's about being honest with others and with ourselves, about what we know, what we hope, and what we're just not sure about. Because once you believe in the teapot, you might start believing in anything. The veil of ignorance. Imagine you're designing a new society from scratch. You get to choose the rules. Who gets what? How power is distributed, how justice works. But there's a catch. You don't know who you'll be in that society. You might be rich or poor, sick or healthy, privileged or oppressed. You don't know your gender, race, intelligence, or background. You're behind what philosopher John Rawls called the veil of ignorance. And the question is, what rules would you create? Not knowing where you'll land. This thought experiment is about fairness. Rawls argued that when we don't know our own position, we're more likely to make fair decisions. We wouldn't create a society that benefits the few, because we might not be one of them. We'd want protections for the most vulnerable, because we could end up in their shoes. This forces us to think about justice without personal bias. Would you design a healthcare system that only works for the wealthy if you might be born poor? Would you support policies that favor one group if you don't know whether you'll be part of it? The veil of ignorance doesn't guarantee agreement, but it changes the way we think. It replaces what's good for me with what's fair for anyone. Rawls believed that people behind the veil would choose a system that maximizes basic rights for everyone, especially the worst off. Not total equality, necessarily, but no one would be left without basic opportunities, safety, and dignity. Critics have argued that people behind the veil might still gamble, choosing a system with huge risks and rewards. Others say we can't ever really think without bias, even in theory. But the veil of ignorance isn't about predicting behavior, it's a tool for perspective. It reminds us that luck plays a huge role in life. You didn't choose your family, your birthplace, or your body. And if you didn't earn those advantages, maybe justice means designing a world where people without them still have a chance. That's the challenge. Can we build systems we'd accept, no matter who we turned out to be? The Chinese room. Imagine you're in a sealed room. Outside the room are people who speak Chinese. They pass messages into the room, sheets of paper covered in Chinese characters. You don't understand Chinese at all. But inside the room, you have a giant book. The book is written in your language. It tells you exactly what symbols to write in response to any message you receive. You copy the symbols carefully. You pass the response back out. The people outside are amazed. To them, it looks like you understand Chinese. Your answers are perfect, grammatically correct, culturally appropriate, sometimes even clever. But do you understand the language? Most people would say no. You're just following instructions. This is the Chinese room thought experiment, introduced by philosopher John Searle in 1980. It's aimed at artificial intelligence. Specifically, it challenges the idea that a machine can truly understand something just because it responds in a human-like way. In the metaphor, the person in the room is the computer. The instruction book is the software. The whole system seems intelligent, but it doesn't actually know what the symbols mean. It's manipulating syntax, not grasping meaning. This gets to a central question in the philosophy of mind and AI. What does it mean to understand? If a chatbot gives convincing answers, does that mean it understands language? Or is it just a really advanced version of the person in the room, following patterns, matching inputs to outputs, with no real awareness? Searle argued that true understanding requires intentionality, a sense of meaning, context, and awareness of what the symbols represent. And that no matter how smart a machine seems, it doesn't have that. Critics pushed back. Some said it's not about the person in the room, but the whole system. The room, the book, the responses together do form an intelligent system. This is called the system's reply. Others asked, if a machine passes every test for understanding, how can we say it doesn't really understand? Isn't behavior all we can observe? After all, how do you know that I understand you? You only see my words and responses. What if all of us are just very advanced Chinese rooms, following biological rules instead of written ones? This leads to deeper questions about consciousness and mind. Is understanding something that only humans have? Could it emerge from the right kind of system, biological or artificial? Or is there something about being alive or having a subjective point of view that can't be reproduced by machines? The Chinese room doesn't give a final answer, it gives a challenge. Can machines really think? Or are they just simulating thoughts so well that we can't tell the difference? Plato's cave. Imagine people who have been trapped in a cave since birth. They're chained, so they can't turn their heads. All they've ever seen are the shadows on the wall in front of them. Behind them is a fire. And between the fire and the prisoners, people walk by carrying objects, speaking, moving. But the prisoners can't see any of that. They only see the shadows cast on the wall. And they think that's all there is. The shadows are their reality. Now imagine one prisoner breaks free. He turns around, sees the fire, and is blinded. He stumbles up out of the cave into the sunlight. At first it hurts. The world is overwhelming. But then he sees real trees, real people, real light. He realizes everything he thought was true was just a shadow. Then he goes back down to tell the others. But they don't believe him. They think he's crazy. They cling to the shadows because that's what they've always known. This is Plato's allegory of the cave from around 380 BCE. It's one of the most powerful metaphors in all of philosophy. It's about how we see the world and how limited that vision might be. The cave represents illusion. The shadows are the stories we're told. The fire is culture, media, politics, tradition, projecting half-truths on the wall. And the journey out of the cave? That's philosophy. It's the painful process of questioning, doubting, and thinking for yourself. The sun represents truth, what's real, beyond appearances. But it's not easy. Truth is often blinding at first. And when someone sees it, they may not be welcomed back. People tend to resist ideas that challenge their reality, especially if it threatens the comfort of familiar illusions. Plato's cave is also about education, not just learning facts, but waking up. Real education isn't about memorizing shadows, it's about turning around. It's about asking, what's behind the image? Who's holding the light? Today, the cave can be anything. Your social feed, your news source, your bubble. The question is, are you watching shadows or turning toward the light? The Demandingness Objection. Imagine you're walking through a city. You pass by a high-end restaurant. People are spending $200 on dinner. Just a few blocks away, someone's struggling to afford food for the day. You're not the one eating at that restaurant, but maybe you have enough money to go out sometimes, or to buy new clothes, or see a concert. Now imagine someone says, instead of spending money on yourself, you should give every spare dollar to people in need, because it will do more good for them than it does for you. Sounds noble. But should morality require that much? Should it ask us to give away most of what we have to help strangers we'll never meet? This is the demandingness objection. It's a challenge to moral theories, especially utilitarianism, that say we're always obligated to do the most good possible. At first, that sounds right. If you can help someone and the cost to you is small, then it seems wrong not to help. That's the logic behind Peter Singer's drowning child argument. If a child is drowning in a shallow pond and all it costs you is ruining your shoes, of course you save them, but Singer takes it further. What if the child is far away and all it costs you is skipping takeout for a week? Morally, what's the difference? You still save a life. So shouldn't you always give when the good you can do outweighs the cost to you? That's the ethical ideal. But here's the problem. That logic never stops. If you spend $20 on coffee this week, but you could have used that money to buy malaria nets or feed a child for days, then you've done something morally wrong. Now extend that. Every vacation, every hobby, every non-essential purchase, all of it becomes morally suspect because it's not the best possible use of your resources. Suddenly, morality demands total sacrifice. Not just being kind, not just helping when it's easy, but constantly putting others' needs above your own comfort. Most people aren't ready for that. Even people who believe in helping others struggle to live that way. So the demandingness objection asks, if a moral theory requires more than ordinary people can realistically follow, is that a flaw in the theory? Or is it a flaw in us? Some philosophers say morality shouldn't be easy. The fact that it's demanding doesn't make it wrong. It just makes it hard. Maybe we're supposed to rise to the challenge. Others say a good moral theory should fit human psychology. If it's too extreme, people will tune it out or break under the weight of guilt. There's also the question of what kind of morality we want. Is morality about being a saint, or about living in a way that balances good with being human? Can a person still be good if they give sometimes, help sometimes, but still live a full life for themselves? The demandingness objection doesn't deny the value of helping others. It just asks whether we're allowed to stop, and where, if we accept that some good is better than none. Then maybe morality isn't about always doing the most good. Maybe it's about doing enough good, enough to care, enough to matter, without burning yourself down in the process. Twin Earth. Imagine a planet exactly like Earth in every way. Same people, same history, same cities. But on Twin Earth, there's one difference. What they call water isn't H2O. It looks and behaves just like water. It's clear, it flows, it quenches thirst, but chemically, it's something else. Let's call it X, Y, Z. You couldn't tell the difference without a lab test. Now imagine that there's a person on Twin Earth who is exactly like you. They speak English, they look like you, they use the word water exactly as you do. But when they say water, they mean XYZ, not H2O. And here's the question. Are you and your twin talking about the same thing when you say the word water? This is the Twin Earth thought experiment, created by philosopher Hilary Putnam in 1975. It's about meaning. It challenges the idea that the meaning of a word comes only from what's in your head. You and your twin have the same thoughts, the same mental image of water, but the stuff you refer to, the actual substance, is different. So even though your minds are identical, the meanings of your words are not. That suggests something surprising. Meaning isn't just in your mind, it depends on the world around you. This is called semantic externalism, the view that what you mean isn't just about what you think, but also about your relationship to things in the external world. The idea matters more than it might seem. Think about scientific terms like gold or tiger. We don't just mean yellow stuff or striped animals. We mean the real thing, the stuff with the right properties, even if we don't know all the details. You might not know that gold is atomic number 79. But when you say gold, you still mean that substance, not just anything shiny. Twin Earth shows that what we mean often depends on facts we don't even know. It also raises questions about identity. If your twin is identical to you in every internal way, but lives in a different world with different references, are you still the same person? What happens when meaning is shaped by the environment? And if our words depend on the world, not just on thought, can we ever fully understand someone who lives in a different world? Twin Earth doesn't deny that thoughts matter, but it reminds us that language is connected to the outside. It's not just a mirror of the mind, it's a tool for navigating reality. And that means what you say and what you mean can't be separated from the world you live in. Laplace's demon. Imagine a mind so powerful, it knows the exact position and motion of every atom in the universe, every particle in every corner of space, every molecule in your brain. Every gust of wind, every tick of a clock, every heartbeat, this mind doesn't guess. It doesn't calculate. It knows. With that knowledge, it could predict the future with perfect accuracy. Not just weather forecasts or chess moves. Everything. What you'll say tomorrow, what you'll eat next week, who you'll marry, and when you'll die. It could also look back and know the past with the same precision. Nothing is hidden. Nothing is uncertain. This is Laplace's demon, a thought experiment proposed in 1814 by the French mathematician Pierre-Simon Laplace. It's not a literal demon. It's a symbol of total knowledge and total predictability. The idea comes from classical physics. Back then, people believed the universe worked like a machine. Every effect had a cause. Every motion followed exact laws. If you knew the starting conditions and the rules, you could calculate everything that would ever happen. In that kind of universe, Laplace said, free will is an illusion. You think you're choosing, but your brain, your body, your environment, your genetics, they're all just atoms obeying physical laws. And those atoms were set in motion long before you were born. So whatever you decide next, maybe it was already determined. That's what makes this idea so disturbing. If Laplace's demon is possible, even in theory, then the future is already fixed. You're not writing your story. You're playing out a script. But is that really how things work? In the 20th century, physics changed. Quantum mechanics showed that at very small scales, events don't follow exact rules. Some things happen by chance, at least as far as we can tell. The exact position of an electron, or when a radioactive atom decays, these can't be predicted with certainty. So some physicists say Laplace's demon is impossible because the universe isn't deterministic after all. But others push back. Just because we can't predict something doesn't mean it's truly random. Maybe there's a deeper order we just don't understand yet. And even if quantum uncertainty exists, it might not affect how our brains work on the larger scale. So, the idea of determinism still stands. And Laplace's demon keeps haunting the background of science and philosophy. If you knew everything right now, every molecule, every force, every tiny detail, could you really predict the future? Would there be any room left for choice? Or would everything you are, your fears, your dreams, your regrets, just be the product of atoms following rules? Some people find comfort in this. If everything is determined, then maybe we're not to blame for our flaws. Maybe we're part of something bigger, an unfolding pattern we don't fully see. But others feel trapped by the idea. What's the point of decisions, of effort, of morality, if everything was always going to happen this way? Laplace's demon doesn't offer answers. It offers a mirror. It asks, if you could know everything, would you want to? And if the future is already written, what do we do with the feeling that we still have a choice? Brain in a vat. Imagine this. You're not really sitting where you think you are. You're not hearing this through ears or seeing the world through eyes. Instead, your brain is floating in a jar. It's hooked up to a supercomputer. That computer sends electrical signals into your brain, exactly the kind of signals your body would normally send. When you think you're touching something, the computer makes you feel that. When you see light, hear voices, smell coffee, it's all simulated. But to you, it feels completely real. That's the thought experiment. It's called the brain in a vat, and it asks one of the oldest questions in philosophy. How do you know that what you're experiencing is real? Maybe everything you've ever seen, heard, or touched is just a computer feeding signals into your brain. If the illusion is perfect, how could you tell the difference? This might sound like science fiction, but it's not. Philosophers have been asking versions of this question for centuries. In the 1600s, René Descartes asked whether an evil demon might be tricking him into believing in a false world. Today, we replace demons with computers, but the problem stays the same. Can we really trust our senses? Everything you know comes through your senses. Sight, sound, touch, smell, taste. But if those senses can be fooled, then anything built on them might also be false. The brain in a vat challenges something we usually take for granted, that reality is what it seems. Think about dreams. When you're dreaming, you don't usually know it. You can feel things, see things, even think logically, inside a world that isn't real. Only when you wake up do you realize something was off. But what if you never wake up? What if this life is the dream? Now, most people want to say, of course I'm not a brain in a jar. But the point of the thought experiment isn't to say you are, only that you can't prove you're not. And if you can't prove it, how do you know anything at all? One response is to say, maybe it doesn't matter. If your experiences are consistent, meaningful, and let you live your life, why worry about whether they're simulated? Another response is Descartes' own solution. Even if I'm being deceived, there must be something being deceived. I think, therefore I am. In other words, maybe I can't prove the outside world exists. But I can be sure that I exist, because I'm the one asking the question. Still, the brain in a vat remains a powerful reminder. It reminds us how fragile our knowledge really is. And how easily what we call reality could be just a convincing signal, nothing more. Pascal's wager. Imagine someone comes up to you and says, you should believe in God. You ask why. They don't give you a Bible or a miracle. They give you a math problem. This is Pascal's wager, created by the French philosopher and mathematician Blaise Pascal in the 1600s. And it goes like this. Either God exists or God doesn't. Those are your two options. Now you have to decide whether to believe or not. That gives us four possible outcomes. You believe, and God is real. You gain infinite reward, heaven, eternal life. 2. You believe, but God isn't real. You lose nothing. Maybe some time, some rituals, maybe a bit of freedom. You don't believe, and God isn't real. You gain nothing, but you also lose nothing. 4. You don't believe, and God is real. Now you face infinite loss. Pascal's point: if the reward for belief is infinite, and the risk of disbelief is also infinite, then the logical choice, the smart bet, is to believe. Even if the chance of God existing is tiny, the potential reward is so huge that belief becomes the safer gamble. Think of it like a cosmic version of buying a lottery ticket. The odds might be small, but if the jackpot is infinite, even a small chance makes it worth it. Pascal didn't say this proves God exists. He said, if you can't know for sure, you should still bet on belief, because the risk of being wrong is infinite. And in a situation like that, hedging your bets makes sense. But a lot of people have pushed back. One big problem is this: which God are we talking about? Christianity? Islam? Hinduism? Some unknown deity? There are thousands of religions. What if you believe in the wrong one? Or what if the real God only rewards honest belief, not belief chosen out of fear or calculation? Another issue is sincerity. Can you really choose to believe something just because it's a better bet? Belief isn't a light switch. You can't flip it just because it's useful. You either believe or you don't. Pascal anticipated this. He said, even if you don't believe yet, you can act like you do. Go to church. Say the prayers. Live the moral life. And maybe over time, belief will grow. In modern terms, this is a kind of fake it till you make it argument for faith. But that raises new questions. If you're only doing it for the reward, is it still meaningful? Can a belief based on a gamble still count as true faith? Pascal's wager doesn't work for everyone. Some people reject it because it feels like playing it safe instead of searching for truth. Others find it useful, not as a proof, but as a way to think about risk and meaning. After all, we make bets like this in life all the time. We take jobs, move cities, trust people, not because we know the outcome, but because the possible reward is worth the uncertainty. Pascal's wager just asks, what if the biggest risk is not believing? The problem of evil. Think about this question. If God exists, and God is all-powerful, all-knowing, and perfectly good, why is there evil in the world? Not just little things like bad traffic or annoying weather. Real suffering, war, disease, injustice, natural disasters. If God could stop those things and wants the best for us, why doesn't He? That's the problem of evil. It's one of the oldest and most difficult arguments in philosophy and theology. The logic seems simple. If God is all-powerful, He can stop evil. If God is all good, He would want to stop evil. But evil exists. So either God is not all-powerful, not all good, or doesn't exist. This argument doesn't try to prove God is bad. It tries to show that there's a contradiction between how people define God and the world we actually live in. Philosophers call this a logical problem, when two ideas that should fit together don't. But not everyone agrees that this problem proves anything. Some theists respond with a defense. Maybe evil exists because God gave us free will. For us to have real choices, we must be able to choose wrong. If God stopped all evil, we'd just be puppets, programmed to behave but not truly free. This is called the free will defense. It says evil is a side effect of freedom, but this defense mostly applies to human-caused evil. What about suffering from earthquakes, cancer, diseases that kill infants? That's called natural evil. Pain not caused by people but by the world itself. Why would a good God create a world with that kind of suffering? Another response is called soul-making. The idea is that struggle builds character. Pain teaches empathy. A perfect, painless life might not lead to growth or moral strength. But this raises new questions. Do we really need this much suffering to learn? Couldn't an all-powerful God teach us in a gentler way? Some thinkers go further and say the problem of evil shows that if there is a God, He may not be the kind we imagine. Maybe God exists, but isn't all-loving. Or maybe goodness means something totally different at a divine level. Others say the problem only looks like a contradiction because we don't see the whole picture. Maybe there's a purpose to suffering we simply can't understand, but for many this doesn't satisfy. Because the pain is real, the questions are real. The problem of evil isn't just a puzzle on paper, it's personal. For some it leads to doubt, for others it deepens faith by pushing them to wrestle with the hardest parts of belief. There's no easy answer. And maybe that's the point. The problem doesn't go away. It just forces us to ask, if we believe in a good and powerful creator, how do we explain a world that often feels the opposite? The drowning child. You're walking through a park on your way to work. You pass a shallow pond. Suddenly, you see a child in the water, struggling, clearly about to drown. You're wearing expensive clothes. You'll be late for work, but if you wade in, you can save the child easily. Do you save them? Almost everyone says yes. You wouldn't even think twice. That's the point of the thought experiment. It was introduced by philosopher Peter Singer in 1972, and here's the twist. If you'd save the drowning child right in front of you, why don't you act the same way when the child is far away? Every day, children die from preventable causes: hunger, disease, lack of clean water. A few dollars, the price of a coffee or a pair of shoes, could literally save a life through a reliable charity. So why don't we treat it like an emergency? That's the ethical challenge. From a moral point of view, distance doesn't matter. If we can help someone and the cost to us is small, shouldn't we do it, whether the person is next to us or halfway around the world? Singer argues that our everyday choices, what we buy, what we donate, what we ignore, are moral decisions, even if they don't feel like it. And the standard we use to justify walking past faraway suffering wouldn't hold up if the child were right in front of us. Some people respond by saying, "It's different when you're there in person. If everyone helped, I wouldn't need to." Or, "I can't save everyone." But Singer's point is sharper than that. He's not saying we must sacrifice everything. He's asking, if it's wrong to let one child drown, why is it acceptable to let many suffer just because they're not visible? The drowning child doesn't try to make you feel guilty. It tries to show how uneven our moral reactions are. We don't always act based on reason. We act based on what's close, what's seen, what's urgent, but the numbers don't care about geography. A child's life is worth the same, whether it's in front of us or across the ocean. That's the uncomfortable truth this thought experiment forces us to face. Tragedy of the Commons. Picture a village. In the center there's a grassy field, the commons. Everyone in the village can use it. It belongs to no one, and everyone relies on it. Shepherds bring their sheep to graze. 1 flock, 2 flocks, then more. Each shepherd thinks, if I add 1 more sheep, I get more profit. It's just 1. No big deal. But everyone thinks that. More sheep arrive. The grass doesn't grow back fast enough. The commons degrades. Soon it's barren. And now nobody wins. This is the tragedy of the commons, first written about by ecologist Garrett Hardin in 1968. And it's more than a story about sheep. It's a deep problem in collective rationality. The idea is simple. When individuals act in their own best interest, using a shared resource, they can end up destroying that resource for everyone. What makes sense for the one becomes disaster for the many. And it applies everywhere: overfishing in oceans, pollution in the air, traffic on highways, spam in your inbox, carbon in the atmosphere. Each person's action seems harmless on its own. But together, the system breaks. And here's what's tricky. Even if everyone knows the collapse is coming, it can still happen, because each person still has the same incentive. Better to take what I can now before someone else does. That logic is hard to resist. It's rational, but when everyone thinks that way, the commons collapses anyway. So how do we fix it? Hardin suggested 2 main options. 1, pointization, divide the resource, make everyone responsible for their own part. If it's yours, you have reason to protect it. But not all commons can be divided. You can't slice up the ocean or the air. 2, regulation, a rule, a limit, a tax, something external to control behavior. But that raises questions. Who enforces it? What's fair? What if some players ignore the rules? And what about trust? Even if you care, you might worry others don't. And that fear drives people to defect, to take more, just in case. Economists call this a coordination problem. Everyone would be better off cooperating. But no one wants to be the only one who sacrifices. That's the tragedy. It's not caused by evil. It's caused by good people following perfectly rational incentives that happen to be badly aligned. The real villain isn't selfishness, it's the structure of the game. But not all hope is lost. Nobel Prize winning economist Elinor Ostrom studied real-life communities that avoided the tragedy. She found that it is possible without central control or private property. People can manage shared resources sustainably, but it takes certain things: clear boundaries, strong communication, trust, local enforcement, a sense of shared identity. In other words, it's not just about rules, it's about relationships. When people feel ownership and connection, they cooperate. When they feel anonymous or distant, they exploit. The tragedy of the commons is a warning, not just about sheep or grass or climate. but about what happens when we treat shared systems like they're someone else's problem, because when the commons collapses, it doesn't just affect them, it affects everyone, including you. The infinite library. Picture a library, but not just any library. This one is infinite. It stretches in every direction forever. Every book in this library is exactly 410 pages long. Each page has the same number of characters, letters, punctuation, spaces, all arranged randomly. At first, most books are nonsense, inches of jumbled letters and meaningless words. But if you look long enough, something strange happens. Somewhere in this library, there's a book that contains the complete history of your life, down to this very moment. Another book holds your future. Another tells the true laws of the universe. Another is one letter off. And another lies. This is the thought experiment Borges imagined in his story, The Library of Babel. It's not a puzzle to solve. It's a mirror held up to infinity, language, and knowledge itself. If you have a system that includes every possible combination of symbols, then everything is in there, all truth, all fiction, all contradictions. But here's the problem. When everything exists, how do you find anything? In a sea of noise, meaningful information becomes nearly impossible to locate. Imagine knowing the perfect book is out there, but not knowing where. Worse, imagine finding a book that looks true but is just close enough to be wrong, or one that gives you hope but is pure fiction. The infinite library becomes a metaphor for many things. For the internet, for data, for randomness, for how we search for truth in a chaotic world. It also raises a deep question in philosophy and math. Is the universe more like a machine that follows rules, or more like a library where every possibility already exists, just waiting to be read? In this model, knowledge isn't discovered, it's found, already written, already there. We're just wandering through the shelves, hoping to stumble on something real. But in a place with every answer, there's also every lie. Borges even suggests that some people in the library go mad. Some become fanatics, convinced they've found the truth. Others despair, certain they never will. And some destroy books to try and reduce the chaos. The infinite library becomes not just a place, but a test. How do you live in a world where truth is buried in infinity? What guides you, logic, belief, luck, or do you stop searching altogether? The paradox of the heap. You have a single grain of sand. No one would call that a heap. You add another grain. Still not a heap. Then another, and another. At some point, maybe after hundreds or thousands, you end up with what clearly looks like a heap. But where exactly did it become a heap? That's the paradox. It's called the Sorcerer Paradox, from the Greek word curated, meaning heap. It goes like this. If one grain isn't a heap, and adding just one grain can't turn it into a heap, then adding one grain over and over should never make a heap at all. But obviously, that's not true. At some point, it is a heap. So where does it change? The Sorcerer Paradox isn't about sand, it's about vagueness. Words like heap, bald, tall, rich, old, these are all vague terms. They don't have sharp boundaries. If you pull out one hair, someone isn't suddenly bald. But pull out enough, and they are. So how many hairs is bald? How much money is rich? How many years make someone old? There's no exact point. And yet we use these words all the time, often in serious situations. In law, in ethics, in medicine, whether someone qualifies as disabled or poor, or a minor or dangerous, these can all depend on vague definitions. That's what makes this paradox important. Because it forces us to ask, can something change by degrees, but never have a clear turning point? And if so, how do we reason about it? Some try to solve this with logic. One approach is called fuzzy logic. Instead of saying something is either heap or not heap, fuzzy logic assigns degrees. Maybe 1 grain is 0% heap. 1,000 grains is 100%. In between, there's a gradual slope. That's useful in computers and AI. where shades of gray can be modeled mathematically. Another approach is supervaluationism. It says that vague terms don't need exact cutoffs, but we can still reason clearly by looking at all the precise versions that could work. A third strategy is to just admit that language isn't perfect. Some philosophers argue that vagueness is part of how humans deal with complexity. We evolved to think in loose categories, not exact boundaries, and maybe that's okay. The Trolley Paradox isn't trying to destroy language, it's trying to show us its limits. When we act like every concept has a clear edge, we can make bad decisions. The world isn't always black and white, it's mostly shades of kind of. Nozick's Wilt Chamberlain argument. Imagine a society where wealth is perfectly equal. Everyone starts with the same amount of money. It's fair, balanced. Now imagine a famous basketball player, Wilt Chamberlain. He's incredible. People love to watch him play. So a deal is made. Anyone who wants to attend his games can choose to pay 25 cents extra, which goes straight to Wilt. 1 million people show up. Each pays the 25 cents. At the end of the season, Wilt has made $250,000, and now he's much richer than everyone else. The question is that unfair? This is Nozick's Wilt Chamberlain argument from philosopher Robert Nozick's book Anarchy, State, and Utopia, and it challenges a basic idea in political philosophy, that a just society must be an equal one. According to Nozick, that's not necessarily true, because this situation started with perfect equality. Then people made free choices to give some of their money to Wilt in exchange for entertainment, and that voluntary process led to inequality. So if we want to restore equality, we'd have to take money away from Wilt. But why? He didn't steal it. No one was forced. Everyone got what they wanted. Nozick argues that a system based on freedom will naturally lead to inequality because people have different talents, goals, interests, and opportunities. And if you try to force equality after that, you're punishing people for acting freely. You're telling them, you can spend your money however you like. But if you do and someone benefits too much, we'll take it back. That's not justice. Nozick says, that's control. His argument is simple but powerful. You can have freedom or equality, but you might not be able to have both. The more you try to enforce equal outcomes, the more you have to interfere with people's choices. And at some point, that stops looking like freedom at all. But critics push back. They ask, what if Wilt only got so popular because he started with better opportunities? What if some people never even had a chance to get in the game? What if the system seems voluntary, but the options are deeply unequal from the start? This is where the deeper argument lies. Nozick believes in what he calls entitlement theory. If you got something through just means, and people gave it to you freely, you're entitled to keep it. But others say, justice isn't just about how we get what we have. It's about why some people keep ending up on top, while others are always stuck below. Nozick admits that inequality can feel unfair, but he says, if you believe people own their lives, their talents, their labor, then the rewards they earn from those things are also theirs. And taking them away, even for equality's sake, means treating people like they don't own themselves. The Wilt Chamberlain argument doesn't say inequality is always good. It says freedom leads to difference, and that forcing equal results may cost more than we realize. In the end, it comes down to this: what matters more, fair outcomes or free choices? And are we willing to sacrifice one to protect the other? Schrödinger's cat. Imagine a sealed box. Inside the box is a cat. Along with the cat, there's a small radioactive atom, a Geiger counter, a vial of poison, and a hammer. Here's how it works. If the atom decays, just by chance, it triggers the Geiger counter. The counter sends a signal. The hammer falls. The vial breaks. The poison is released. The cat dies. But if the atom doesn't decay, nothing happens. The cat stays alive. Here's the twist. In quantum mechanics, until the atom is measured, it exists in a superposition, a state of both decaying and not decaying at the same time. So until someone opens the box and checks, the atom is both changed and unchanged. And because the cat's life depends on that atom, the cat is also both alive and dead. That's Schrödinger's cat, a thought experiment proposed by physicist Erwin Schrödinger in 1935. He didn't mean it literally. He was trying to show how weird and counterintuitive quantum mechanics can be when applied to everyday things. In the world of atoms and particles, things don't work like we expect. A particle can be in two places at once. It can spin both left and right at the same time. These aren't metaphors, they're real predictions made by the math and confirmed by experiments. But when we try to scale that up to something big, like a cat, it sounds absurd. Schrödinger wanted people to stop and say, "Wait, what?" and ask, when does something stop being uncertain and become real? Is the cat really both alive and dead? Or is it just that we don't know which until we look? That's the heart of the puzzle. Some interpretations of quantum mechanics say that measurement collapses the superposition. Before you open the box, the cat is in a blur of both outcomes. But the act of observing forces the universe to pick one. Other interpretations say the cat isn't in both states, just our knowledge of the cat is. The cat is always either dead or alive. We just don't know until we check. And then there's the many worlds interpretation. It says that when the atom decays and doesn't decay, the universe splits. In one world, the cat lives. In another, it dies, and both are real. Schrödinger's cat doesn't answer these questions. It raises them. It shows that in the world of quantum mechanics, reality doesn't behave the way we expect. Observation might not just reveal what's true. It might actually change what's true. And that forces us to ask, where does uncertainty end, and where does reality begin? Searle's biological naturalism. In the age of AI, we often hear a bold idea. The brain is just a computer. It takes inputs, processes information, and produces outputs. So, if we can simulate the brain's structure closely enough, if we run the right code on the right hardware, we'll get consciousness right. Philosopher John Searle wasn't so sure. In fact, he argued, you can have a perfect simulation of a brain and still not have a mind. His theory, called biological naturalism, says that consciousness isn't something you can separate from biology. It's not just about processing symbols, it's about being a specific kind of biological system. That's a big claim. Let's break it down. Searle agreed that brains are physical. He didn't believe in souls or magical substances, but he rejected the idea that mind is software. To him, consciousness isn't a program running on a platform. It's more like digestion or photosynthesis. A biological process that happens in living things, specifically in brains. You can simulate a storm on a computer, but it doesn't get wet. You can model a stomach digesting food, but it doesn't break anything down. Likewise, you can simulate consciousness, but that doesn't mean the system is actually conscious. It's just mimicking the behavior. A person inside a room follows instructions to manipulate Chinese symbols without understanding what they mean. From the outside, it looks like the room speaks Chinese. But inside, there's no comprehension. That's how Searle sees AI systems. They might pass language tests, mimic emotions, generate responses, but they don't understand. Because understanding, he says, is tied to something only biological brains can do. This is where biological naturalism gets specific. It says consciousness is real. It's caused by physical processes in the brain, but it's not something you can abstract away from the biology. It's like a flame, caused by chemistry, but you can't run a flame on a circuit board. Searle's critics argue back. They say, but the brain is a biological machine, and if we copy its structure exactly, why wouldn't the copy produce consciousness? Maybe it doesn't matter what the system is made of, only how it's organized. Maybe it's the pattern that matters, not the material. But Searle's reply is simple. If the system lacks the biological capacity to generate consciousness, it won't matter how good the imitation is. It'll behave like a person, but it won't be having experiences. And to Searle, that difference matters more than anything else. Because consciousness isn't just input and output, it's what it feels like inside to be you. And unless your system can produce that, it's not conscious no matter how smart it looks. Biological naturalism doesn't deny the power of machines. It doesn't say AI can't be useful, or impressive, or even emotional in appearance, but it draws a line between simulating a mind and having one. And it reminds us, maybe consciousness isn't something we'll build from silicon. Maybe it's something that grows in blood, in neurons, in the living matter of the brain. Epistemic closure. Suppose you know that your car is in the garage, and you also know if your car is in the garage, then it hasn't been stolen. That's basic logic. So by combining those two things, you should also know your car hasn't been stolen. That's called epistemic closure, a principle in epistemology, the study of knowledge that says if you know something and you know it, logically leads to something else. Then you also know that second thing. It seems obvious. If I know A, and I know A implies B, then I should know B. But now let's try it with something stranger. Suppose you say, I know I have two hands. And you also know, if I have two hands, then I'm not just a brain in a vat being tricked into thinking I do. So according to epistemic closure, you should also know, I'm not a brain in a vat. But hold on. That's a big claim. Can you really know that you're not a brain in a vat? Can you rule out with certainty the possibility that this is all a simulation or a dream or an illusion? If you can't, then by the closure rule, maybe you don't really know you have two hands either. That's how skepticism enters the picture. Because closure means your knowledge is connected, logically, but that also means one weak link can break the whole chain. If you can't rule out the weird stuff at the bottom, you might not be allowed to claim the obvious stuff at the top. This is sometimes called the skeptical challenge to closure. Some philosophers defend closure. They say, yes, you know you have two hands. That's stronger than the possibility of being in a simulation. And since you know that, you can also reject the crazy scenarios. Others go the opposite way. They say, no, you don't really know you have two hands because you haven't ruled out all the alternatives. And if that sounds ridiculous, that's kind of the point. Epistemic closure turns simple, everyday knowledge into a trap. It pulls hidden assumptions up to the surface and says, if you believe this, you're logically committed to all of this too. It's like a contract with fine print. Knowing one thing drags along everything it's logically tied to, and if any part of that chain is shaky, the whole structure starts to wobble. This isn't just an academic game. It has real implications for how we build belief systems. If we accept closure, then we have to be extremely careful about what we claim to know. Every belief has consequences, logical children that we're stuck raising, whether we like them or not. But if we deny closure, if we say you can know A without knowing B, even if A implies B, then logic starts to break down. Knowledge becomes disconnected. You get beliefs that don't follow through. That's why this puzzle matters, because either way, you lose something. Keep closure, and you might have to doubt everything. Drop closure, and you risk inconsistency. So maybe the real question isn't, do I know I have hands? Maybe it's, how far am I willing to let my knowledge carry me before I start pulling back? The drunkard's walk. Imagine a man walking home late at night after a few too many drinks. He's not thinking clearly. He doesn't walk in a straight line. Every step he takes is a bit random. Sometimes he steps left, sometimes right. Maybe even turns around without realizing. After a while, he's wandered a long way. But it wasn't planned. There was no goal. He didn't even know where he was going. That's what we call a random walk, or more memorably, the drunkard's walk. And while it sounds simple, this idea shows up everywhere, from physics to finance to philosophy. It's used to describe how things move, how they change, and how chance plays a bigger role than we think. Here's why it matters. Think about someone who becomes super successful, maybe a famous actor or a tech billionaire. We often look at their story and say, they worked hard, they were smart, they made the right choices. And maybe they did. But what if part of their success was just that? They happened to step in the right direction at the right time. Just like the drunk man who by pure luck ended up at his front door. The drunkard's walk reminds us that even if each step seems small and random, they add up. And sometimes they lead to places we never expected, good or bad. In science, random walks explain how molecules move in a gas. In the stock market, they describe how prices go up and down, often with no clear reason. Even your life can feel like a random walk. You try things, you make choices. Some go well, others don't. But sometimes, where you end up has less to do with a master plan and more to do with chance. That doesn't mean your choices don't matter. It just means chance is always in the picture, whether we see it or not. And that leads to two important ideas. First, we often give too much credit for success. When someone makes it, we imagine they did everything right, but they may have just gotten lucky. Maybe they were in the right place. Maybe they knew the right person. Maybe they made a risky move that just happened to work. Second, we often give too much blame for failure. Someone might have worked just as hard, been just as smart, but their steps led them somewhere else. Maybe they stumbled early. Maybe they didn't get noticed. The drunkard's walk helps us be more humble. It reminds us that success and failure aren't always fair reflections of effort, and that life is full of unexpected twists, even when we try our best. That doesn't mean we give up. It means we stay realistic. We stop thinking we can control everything, and we stop judging others as if they could control everything too. Because even when you do everything right, randomness still plays its part. One small change, a different school, a missed opportunity, a lucky break, and the path looks completely different. Like the drunk man, you keep walking, but you don't always know where you'll end up. Some people might look at where you are and think, wow, you were meant to be here. But the truth might be simpler. You made your choices, yes, but chance walked with you, just like it walks with all of us. The trolley problem. A trolley is speeding down the tracks. Ahead, 5 people are tied to the rails. You're standing next to a lever. If you pull it, the trolley will switch tracks. But on the other track, there's one person tied down. If you do nothing, 5 die. If you pull the lever, 1 dies because of you. What do you do? This is the trolley problem. At first, it seems like a math problem. 5 lives outweigh 1, but the moment you act, you're responsible for a death. Some people refuse to pull the lever, believing killing is always worse than letting die. Others see it as a moral obligation to minimize harm. But it doesn't stop there. What if you're on a bridge above the tracks? A large man is standing next to you. If you push him onto the track, his body will stop the trolley. He dies, but the 5 survive. Most people say no. Why? The numbers are the same. 1 dies, 5 live. But in this case, you have to touch the person. It feels more like murder. This shift from pulling a lever to pushing a person exposes a deep divide in moral philosophy. Consequentialists, especially utilitarians, focus on outcomes. Fewer deaths equals a better result. Deontologists, following philosophers like Immanuel Kant, argue that some actions are wrong in themselves, regardless of outcomes. Killing an innocent person is always wrong, even to save others. The trolley problem isn't about trains, it's about moral boundaries. Is it ever right to harm one person for the greater good? Real-life versions of the problem exist everywhere. In medicine, when allocating limited resources. In war, when targeting one area might prevent larger loss elsewhere. In autonomous vehicles, when programming a car to decide between 2 bad outcomes. There are even cultural differences. Studies show people from different societies make different choices. Moral intuition is not universal. Variations of the scenario keep testing our limits. What if the person on the other track is a child or your own family? What if the 5 are strangers, but the 1 is someone you love? What if you're required to decide instantly without time to think. The trolley problem stays with us because it's simple but unsolvable. It shows that our moral code isn't just a list of rules or a numbers game, it's a tension between principles and consequences, between logic and emotion. And it reveals how easily that tension breaks, under pressure, under fear, or in the face of loss. Zeno's paradoxes. Imagine you're in a race. You're running toward the finish line. Seems simple, but according to Zeno, a Greek philosopher from 2,500 years ago, you'll never get there. Why? Because before you can reach the finish line, you have to get halfway there. Then you have to go half of that remaining distance, then half of that, and so on forever. Each time you're cutting the distance in half, getting closer, but never quite reaching the end. That's Zeno's first paradox. It's called the dichotomy, and it suggests that motion is impossible. Because if you have to complete an infinite number of steps to reach any destination, how could you ever finish? But we do reach the finish line. People run races every day. So what's going on? Zeno wasn't bad at math. He was trying to show that our common sense about space and time might be flawed, or at least incomplete. Let's try another one. Achilles, the fastest runner in Greece, is racing a slow-moving tortoise. To be fair, the tortoise gets a head start. Now Achilles starts running. He reaches the point where the tortoise began. But by then the tortoise has moved forward a little. Achilles runs there, but the tortoise has moved again. No matter how fast Achilles runs, the tortoise always stays ahead. That's the Achilles paradox. It seems to say that a faster runner can never catch a slower one, which obviously isn't true in the real world. So why do these paradoxes matter? Because they reveal a tension between infinite division and finite action. Mathematically, we now know that you can add up an infinite number of smaller and smaller pieces and still get a finite result. For example, if you keep halving the distance, 1/2, 1/4, 1/8, and so on, those numbers add up to 1. So you can cross a full distance, even with infinite steps, as long as each one gets smaller fast enough. Calculus and limits, developed thousands of years later, help solve Zeno's paradoxes mathematically. But Zeno's real question wasn't about racing. It was about how we understand the world. Is space made up of tiny indivisible bits, like pixels? Or is it continuous, infinitely smooth, with no smallest part? What about time? Does it flow in a smooth stream? Or does it tick by in tiny moments we just can't perceive? These questions still matter today, in physics, in cosmology, even in debates about how computers model reality. Zeno's paradoxes remind us that simple things, like walking, moving, or passing time, can fall apart under close examination. Just because something works in practice doesn't mean we understand it in theory. Buridan's issue. Imagine a donkey. It's hungry and thirsty. Right in front of it, on the left, there's a pile of hay. On the right, there's a bucket of water. Both are equally close, equally tempting. The donkey can't decide which to go to first, food or water. It weighs the options, compares them, but they're exactly the same. So it stays put, paralyzed by perfect balance. And eventually, it dies. That's the story of Buridan's ass, a thought experiment from the Middle Ages named after philosopher Jean Buridan. It sounds like a joke, but it's meant to ask a serious question: what happens when your choices are perfectly equal and your decision-making process depends only on logic? If you have no reason to choose one option over another, can you still choose at all? On the surface, it's a paradox about indecision, but underneath, it's about free will. If we're purely rational, if every decision we make is based on reasons, then what do we do when there's no reason to go one way or the other? Shouldn't we be able to just pick? But if the mind needs a reason and there isn't one, doesn't that trap us? This is where the donkey becomes a mirror, because humans do this too. We get stuck between job offers, colleges, career paths, relationships, or even dinner choices. We think, if I just had one good reason, I'd decide. But what if there is no better option? What if they're exactly equal or too close to tell? Some people shut down. They delay, overthink, freeze. Not because the decision is hard, but because it feels like the wrong decision would be a mistake. That's the hidden danger. We expect our choices to be logical, but real life doesn't always give us clean comparisons, and sometimes logic alone can't help us. Philosophers have debated what this thought experiment really shows. Some say it proves free will must exist, because even if two options are identical, we can still choose. Something inside us breaks the tie. Not reason. Something else, intuition, will, randomness. Others argue the donkey wouldn't actually die. That in real life, tiny hidden differences, like a shadow or a scent, would make one side slightly more appealing, and the choice would happen. The point isn't whether a donkey would really starve. It's that pure logic can fail when options are perfectly balanced, and when that happens, we need something else to guide us. Sometimes it's emotion, sometimes it's instinct. Sometimes it's just flipping a coin. But the deeper idea is this: if we always wait for the perfect reason to act, we might never act at all. And that's not just a problem for donkeys. It's a problem for anyone who gets stuck trying to make the right choice when maybe there isn't one. Maybe what matters is not which option you pick. Maybe what matters is that you pick before the moment passes. The Grandfather Paradox. Imagine you build a time machine. You set the dial, flip the switch, and travel decades into the past, before you were born. Once you're there, you meet your grandfather. And for some reason, let's say the fate of the universe depends on it, you stop him before he ever has children. That means your parent is never born. And that means you're never born. But if you're never born, you couldn't have gone back in time to stop him. Which means your grandfather lives. Which means you are born, and now can go back in time again, and stop him, and not be born. And around it goes. That's the Grandfather Paradox, a time travel loop that breaks logic. It's one of the most famous thought experiments about time, causality, and contradiction. At first, it just seems like a sci-fi puzzle. But the deeper you go, the stranger it gets. Because what the paradox really shows is this: if you can change the past, then cause and effect starts to collapse. Normally, we think of time like a line. One event leads to another. But time travel lets you jump backward and change something that caused you to exist. And once that happens, logic breaks down. How can something both happen and not happen? Philosophers and physicists have offered different ways to deal with this. One idea is called the consistency principle. It says, maybe you can go back in time, but you can't change anything in a way that causes a contradiction. No matter what you try, something will always stop you. Maybe the gun jams. Maybe your grandfather escapes. The past resists change. This turns time into something more like a locked puzzle. You can visit it, but you can't break it. Another approach says, if you do change the past, you create a branch, a new timeline. In this view, you don't erase your own birth. You just cause a new version of history to split off. In that version, you never existed. But in the original one, you still do. This is the multiverse theory, often used in science fiction. It avoids contradiction by saying everything that can happen does happen, just in a different world. But not everyone is satisfied with that. Some say time travel itself might be impossible, not because of physics, but because of logic. If the past can't be changed without contradiction, then maybe the universe just doesn't allow it. The Grandfather Paradox doesn't prove time travel is fake, but it shows that if time travel is real, it can't work the way we imagine. You can't rewrite your own origin story without tearing a hole in causality. So maybe the real question isn't, can we go back in time? It's, can the past ever really be undone? The Liar Paradox. Read this sentence. This statement is false. Sounds simple, but let's take it seriously. If the sentence is true, then what it says must be the case. But it says it's false. So if it's true, it's false. But if it's false, that means it isn't true, which means the statement is not false, it's true. So if it's false, it's true. Either way, you're stuck. This is the liar paradox, a sentence that flips back and forth between truth and falsehood, breaking the very logic it uses. And it's not just a brain teaser, it's a deep problem in the foundations of logic, language, and mathematics. Versions of it go back at least 2,500 years to the Greek philosopher Epimenides, who was said to have claimed, "All Cretans are liars," while being a Cretan himself. The issue isn't just that he might be lying, it's that the sentence refers to itself. And that kind of self-reference is where logic starts to crack. The liar paradox seems harmless. It's just one sentence. But once you allow statements that talk about their own truth, strange things happen. It's like a mirror reflecting itself. You get a loop, an infinite recursion. And the normal tools of logic, true or false, valid or invalid, stop working. This caused huge problems for mathematicians in the early 20th century. They were trying to build a system where all mathematical truths could be proven from basic rules. But the liar paradox exposed a dangerous idea: that a system powerful enough to describe truth could also describe its own limits and break itself. This led to Gödel's incompleteness theorems, which proved that any system rich enough to include arithmetic will contain true statements that can't be proven within the system. In other words, logic has holes. No matter how perfect a system looks, there will always be truths that it can't reach. The liar paradox is the seed of that realization. And it keeps popping up in different forms. Computers crash when code gets stuck in a recursive loop. Legal systems struggle with self-contradictory rules. Even social dynamics can echo the paradox, like when someone says, "I'm always lying," or "Don't trust anything I say." What do you do with a sentence that cancels itself out? Philosophers and logicians have tried different approaches. Some say we should avoid self-reference entirely. Others say we need more than two truth values. Maybe a sentence can be both true and false. Or neither. This is where paraconsistent logic and fuzzy logic come in, systems built to handle contradiction without exploding, but none of them fully dissolve the paradox. It still lives at the edge of what we can say and prove. The liar paradox teaches us something uncomfortable. Even simple language can create deep confusion. And some questions can't be answered with a clean true or false, not because we lack information, but because the question itself bends logic too far. Sometimes the problem isn't the answer. It's the sentence. The absent-minded driver. Imagine you're a driver on a late-night road trip. You're tired. You've made this trip before. But tonight, you're a little out of it. At a certain point, you'll come to an exit ramp. If you take the first exit, you'll end up in a sketchy, unsafe area, somewhere you don't want to be. But if you skip that one and take the second exit, you'll get home safely. If you miss both, you'll end up lost in the middle of nowhere. Here's the problem. By the time you reach an exit, you don't remember if it's the first or the second. You can't tell them apart. And they both look exactly the same. So when you arrive at an exit, you have to decide, take it or keep driving. This is the absent-minded driver thought experiment, introduced by philosopher Robert Stalnaker, and it reveals something strange. In some situations, being perfectly rational might actually lead you to a worse outcome. Let's break it down. Before the trip starts, you know the layout. If you take the first exit, bad outcome. If you take the second exit, best outcome. If you miss both, also bad. So what's the best plan? If you could remember which exit you're at, it'd be easy. Take the second, skip the first. But you can't. You're absent-minded, just like the name says, so you have to choose a rule in advance. Maybe you decide, every time I see an exit, I'll take it, or every time I see an exit, I'll pass it. Or maybe something more complex, like, I'll flip a coin. But here's the twist. The strategy that seems logical, take the second exit, is now impossible to follow because you don't know which one you're at. You don't have the information. So your strategy can't depend on what exit it is. It can only depend on what to do in any identical-looking moment. Some versions of the problem make it even trickier. Imagine this setup. If you take the first exit, you get a small reward, say $100. If you take the second, you get a larger reward, say $1,000. But if you miss both, you get nothing. What's the best move? Intuitively, you might say, skip the first, take the second. But again, you don't know where you are, and if you always pass on exits, there's a good chance you'll miss both. But if you always take the first exit you see, you might end up settling for the smaller reward every time. So what's optimal? Weirdly, the answer might be, take the exit you see, but only with a certain probability, like 70% of the time. Take it. 30% of the time, pass. That randomness gives you the best average outcome across all possible positions. It feels bizarre, but when your memory fails and every decision point looks the same, this kind of probabilistic reasoning becomes the only logical path. The absent-minded driver shows us how fragile rationality can be. It's easy to plan when you know exactly where you are. But once you introduce uncertainty about context, even simple decisions get weird, and sometimes the smartest move is to act randomly. That's not just theory. In real life, similar patterns show up in game theory, economics, and AI. Systems with limited memory or incomplete information have to use strategies instead of precise plans. Because in some moments, you don't need more intelligence. You need a coin flip. The Barber Paradox. In a small town, there's a rule about shaving. The town has one barber. He's responsible for shaving all the men in the town, but only those who do not shave themselves. If a man shaves himself, the barber leaves him alone. If a man doesn't shave himself, the barber shaves him. Simple, right? But here's the question. Who shaves the barber? Let's think it through. Option 1. The barber shaves himself, but according to the rule, he only shaves those who don't shave themselves. So if he shaves himself, he's not allowed to shave himself. That's a contradiction. Option 2. The barber does not shave himself, but the rule also says he shaves everyone who doesn't shave themselves. So if he doesn't shave himself, he's supposed to shave himself. Another contradiction. No matter what you choose, the rule breaks. That's the Barber Paradox, a logical puzzle made famous by the mathematician Bertrand Russell in the early 20th century. It's a small story, but it uncovers a much bigger problem. Self-reference can destroy logic. This wasn't just a fun riddle. It revealed something deeply wrong in how we understood sets, categories, and systems of rules. At the time, mathematicians were trying to build a perfect, consistent foundation for all of math. They thought, if we can define everything clearly enough, if we set up the right rules, there will be no contradictions. But then Russell's paradox arrived. The Barber story is just a simple version of it. The full version asks, is there a set of all sets that do not contain themselves? Just like the barber, this question creates a loop. If the set does contain itself, then it shouldn't. If it doesn't, then it should. Same trap. The paradox showed that even in pure logic, just symbols and rules, you can hit a wall. A place where definitions fold in on themselves and stop making sense. And that shook the foundations of mathematics. It led to massive revisions in how math and logic were structured. People realized you can't just define anything you like. Not if you want consistency. You have to be careful about what is allowed to refer to what. Self-reference isn't always a problem. But if it's built into the core rules of a system without limits, contradictions can appear out of nowhere. You get statements that are neither true nor false. Systems that collapse under their own rules, and questions that can't be answered, not because we don't know the answer, but because the question breaks the logic itself. That's the real insight of the Barber Paradox. It's not about shaving. It's about how easy it is to create impossible situations just by following the rules too closely. Logic is powerful, but it's not invincible. And sometimes the most dangerous contradictions aren't hidden in complexity. They're hiding in the rules that look the most simple. Teletransporter Paradox. Imagine it's the future. You're at the airport, except now, there are no planes. There's a machine, the teletransporter. You step inside, it scans your body down to the atom. It records your exact structure, your brain, your memories, your voice, your heartbeat. Then it destroys your body. Instantly, somewhere else on the other side of the world, or maybe on Mars, the machine builds a perfect copy. The new you wakes up, steps out, continues your life. Same thoughts, same feelings, same plans for dinner. From the outside, nothing is lost. But here's the question. Is that still you, or did you just die and get replaced? This is the Teletransporter Paradox, made famous by philosopher Derek Parfit, and it asks one of the most disturbing questions in philosophy. What is personal identity? What makes you you? Is it your body? Is it your memories? Is it your brain, your personality, your consciousness? If the copy has all of those, then maybe yes, it's still you. After all, you won't notice anything. You'll walk out of the chamber and go on with your day. But remember, the machine destroyed your original body. So are you the one who walked out? Or is that just a new person who thinks they're you? What if the machine malfunctioned? Suppose it scans you, builds the copy, but forgets to destroy the original. Now there are two of you, both with the same memories, both saying, I'm the real one. So who gets your life? Who owns your relationships? Your job? Your dog? More importantly, if the version that wasn't destroyed feels just as real, then maybe the one that is destroyed every other time was dying all along. And we just didn't notice because the copy was so convincing. The Teletransporter Paradox shows how fragile our idea of identity really is. We like to think there's one continuous self, one person moving through time, but this machine challenges. It breaks the link between continuity of body and continuity of self. Some philosophers say identity is just a matter of psychological continuity. If the new you remembers being you, acts like you, and feels like you, then that's enough. The old body doesn't matter. But others say that's not good enough. Because if perfect memory and personality are all it takes, then copies of you could keep popping up. And if identity can be copied, then maybe it was never really fixed in the first place. Maybe you is more of a story than a substance. Parfit himself came to a strange conclusion. He said, identity isn't what matters. What matters is survival in the right way. If your future self remembers you, continues your thoughts, and lives your life, then that's enough. Even if, technically, you ended in the machine. But if that's true, then death becomes a little blurry. If the copy is enough to count as you, then maybe personal identity was never as solid as we thought. Maybe we're less like statues, unchanging over time, and more like waves, shifting, passing through different shapes, but somehow still connected. The Ship of Theseus. Imagine a wooden ship. Over time, the planks begin to rot. One by one, they're replaced until eventually every single piece is new. Here's the question, is it still the same ship? This is the Ship of Theseus, a problem that's been debated for over 2,000 years. It asks what it really means for something to stay the same when all of its parts change. Let's take it a step further. Suppose someone gathers all the original discarded planks and reassembles them into a ship. Now there are two ships. One made entirely of new parts in the same place as the original. Another made of the old original wood, but rebuilt elsewhere. Which one is the real Ship of Theseus? Both have a claim. One preserves continuity. The other preserves material. But intuitively, we hesitate. We want one identity, one answer. This isn't just about boats. The Ship of Theseus is a stand-in for people, objects, nations, even minds. You're made of cells that constantly die and regenerate. After 7 years, almost every cell in your body has been replaced. Are you still the same person? What if your memories fade, your beliefs shift, your identity evolves? At what point do you stop being you? Philosophers split into camps. Essentialists argue that something remains the same only if it keeps some essential core, a soul, maybe, or a pattern. Mereological essentialists claim identity depends on parts, change enough parts, and the object is no longer the same. Perdurantists say objects are four-dimensional, extending through time like a movie, not a snapshot. Identity isn't a single moment, but a continuity of connected stages. Then there's the psychological continuity view. What matters isn't the matter, but the mind. If your thoughts, memories, and personality persist, maybe your identity does too. But these answers all run into edge cases. What if you're gradually replaced with artificial organs, then synthetic neurons? At what point are you more machine than man? What if your memories are uploaded and a perfect digital copy of you wakes up elsewhere? Is that still you? Or is it just a new being with your story? The Ship of Theseus forces us to ask, is identity about material, memory, pattern, or something else entirely? Maybe there's no single answer. Maybe the concept of identity isn't fixed. It's something we project onto change. A way of holding continuity in a world where everything is always in motion. This is the paradox. Even as everything changes, something feels like it stays the same. And maybe that feeling, however fragile, is what we call self. The utility monster. Imagine a creature. Let's call it the utility monster. It's not evil. It's not violent. But it has one strange property. It experiences pleasure more intensely than anyone else. Give it a cookie, and it feels more joy than you would from winning the lottery. Give it $1, and it's happier than 10,000 people combined. No matter what you do, the monster benefits more than you or anyone else. So here's the problem. If we want to maximize happiness in the world, if we believe in utilitarianism, then the logical thing to do is give everything to the monster, all the resources, all the energy, all the attention. Because for every dollar or minute we give to anyone else, we could have made the monster much happier, and that seems wrong. This is the utility monster thought experiment, created by philosopher Robert Nozick, and it's not about monsters, it's about morality. Specifically, it's a critique of utilitarianism, the idea that we should always act in a way that produces the greatest total good. On the surface, utilitarianism sounds kind and fair. Help the most people, minimize suffering, maximize well-being. But Nozick asked, what if doing the greatest good leads to deeply unfair outcomes? What if it means sacrificing everyone else for the sake of one being, just because that being happens to feel things more deeply? Imagine a society that gives 99% of its resources to a single super-sensitive individual. Everyone else lives in misery, but that one person is ecstatic. Total happiness is maximized. But does that world feel just? The utility monster forces us to think about two key ideas. 1.2, should we always maximize total happiness, no matter how it's distributed? 2, is everyone's happiness worth the same? Or do some experiences count more? Most of us have an instinct for fairness. We believe everyone matters, that people deserve a basic level of dignity and care, even if someone else could benefit more. But pure utilitarianism doesn't work like that. It doesn't care who gets the benefit, only that the total benefit is high. So if one being could use resources more efficiently, feel more joy, suffer more pain, then all resources should go to them, and that quickly becomes disturbing. Because suddenly, the more sensitive you are, the more you deserve. And if you feel less, you matter less. That logic doesn't stop with monsters. You could apply it to humans. Should a genius artist or a brilliant inventor get more food, attention, and care because their joy matters more? Should we ignore the quiet, the average, the emotionally flat, because they feel less? These aren't just abstract questions. They show up in real debates about resource distribution, education, healthcare, even animal ethics. Some people argue that animals suffer more intensely than humans in factory farms. Should that give their pain more weight? Or what if future artificial minds can feel vastly more pleasure than we can? Would we owe them everything? Nozick's point wasn't that the utility monster is real, it's that our moral systems can be twisted by edge cases, and if we don't question our principles, we might follow them straight into injustice. The thought experiment doesn't solve the problem, but it forces a hard question. If doing the most good for the world means doing something terrible to individuals, can that really be good? The is-ought gap. You're studying nature. You notice something. Animals compete. The strong survive. The weak don't. It's a fact. But then someone says, therefore, we should let the weak die out. That's nature's way. Hold on. That jump from what is to what ought to be isn't as smooth as it looks. In fact, it might be a mistake. That's the core of the is-ought gap, a problem raised by Scottish philosopher David Hume in the 1700s. He noticed that people often talk about the world one way, then suddenly shift to moral conclusions. They start by describing how things are, facts, data, natural behavior, and then jump to what people should do. But Hume said, you can't do that, at least not without adding something extra. You can describe reality all you want, but facts alone can't tell you what's right or wrong. That shift from is to ought needs a bridge, and most people never build it. Let's try another example. Imagine someone says, people lie all the time, so lying must be okay. That's a move from a fact. Yo, people lie to a value. Yo, people lying is okay. But something's missing. Just because something happens often doesn't mean it's good, and just because something is natural doesn't mean it's moral. Hume's point is that you need a reason to go from one to the other. You can't smuggle in a value just because you feel like it fits, and this has huge consequences. It means that science alone can't give us ethics. Science can describe the world in incredible detail. It can tell us what exists, how things work, what causes what, but it can't tell us what we should care about. For example, science can show that helping others releases dopamine. But should we help others just for a brain chemical boost? Science can tell us that some people are born with traits that give them an advantage. But should society be built to reward those traits above all others? The is-ought gap says you need something more than facts to answer those questions. You need values. And values don't come from microscopes or data. They come from philosophy, culture, compassion, reasoning. Some thinkers tried to close the gap. They said, if we agree on some basic values, like reducing suffering, then we can use facts to figure out what we ought to do. But even then, the first step, the ought, still isn't coming from facts. It's coming from a moral starting point. Once you have that, facts become tools. But without it, you're just describing the world, not guiding behavior. The is-it gap isn't just a trick of language, it's a warning. If you want to make a moral claim, don't pretend it's a fact. Show your reasoning. Admit your assumptions. Build the bridge. Don't skip it. Because when people confuse is with ought, they can justify almost anything, from injustice to cruelty to silence, all while sounding scientific. But if facts can't tell us what's right, then maybe we're more responsible for our values than we like to admit. The problem of other minds. Look at the people around you, your friends, your family, strangers in a crowd. They laugh, they cry, they tell stories, complain, hug, argue, get excited, fall asleep. You assume they're conscious, like you, that they have thoughts, memories, emotions, that behind their eyes, there's someone home. But here's the haunting question. How do you actually know that? You can't see their minds. You see behavior, hear words, watch reactions, but you never experience their experience. Maybe they're just really good at pretending. Maybe they're complex biological machines, acting conscious without being conscious. This is the problem of other minds, a classic question in the philosophy of mind. It's not about science fiction or paranoia. It's about the limits of certainty. You know your own mind directly. You don't guess that you feel pain, you just do. You don't infer that you're seeing red. You see it. Your thoughts are private, and first person. But when it comes to other people, all you have is evidence. Facial expressions, body language, speech. And from that, you assume there's a conscious person inside. That assumption feels safe. After all, other people act like you. And it would be absurd to say they're all zombies. But here's the catch. That assumption is not provable. You can never directly access another mind. Even if someone says, "I'm in pain" or "I feel happy," you're still taking their word for it. That doesn't mean they're lying, but it means your belief is based on behavior, not internal experience. Philosophers call this the problem of inference to other minds. We do it automatically. But logically, it's a leap, and that leap opens the door to strange possibilities. What if some people aren't conscious? What if machines could act conscious without feeling anything? What if animals are deeply conscious and we've ignored it because they don't speak our language? These aren't just puzzles, they have moral weight. Because we treat others differently, depending on what we believe they feel. If someone is in pain, we try to help. But if we think they're just reacting mechanically, no feelings, no awareness, we might not care. So when you can't prove another being is conscious, but you suspect they are, how should you treat them? Some philosophers say the best we can do is a kind of empathetic bet. Assume others are conscious, because if they are, it matters, and if they aren't, no harm done. This idea shapes how we approach animals, children, people with cognitive disabilities, even artificial intelligence. Should we treat them as having minds, just in case? Or should we wait for proof that may never come? The problem of other minds also flips inward. Because if you can't access other minds, then no one else can access yours. No one knows what it feels like to be you. They might guess, they might try, but your experience is your own. And that creates a strange kind of loneliness built into consciousness. You are the only direct witness to your own mind. Everyone else sees the outside. The problem of other minds won't go away. But maybe it can make us more careful, more humble about what we claim to know, and more kind, just in case there's someone really there behind the eyes we see. The problem of induction. The sun has risen every day of your life. You've seen it, felt it, relied on it. So tomorrow you assume it will rise again. Seems like a safe bet. But here's the problem. How do you know it will? Not hope, not guess, not assume. No, you might say it always has. But that just means it's happened before, and that's where the trouble starts. This is the problem of induction, made famous by the philosopher David Hume. It challenges a basic part of how we think, that the past can tell us about the future. That patterns repeat, that nature is consistent, that if fire burned me yesterday, it'll burn me tomorrow, that if gravity pulled me down last year, it'll pull me down next year. This is called inductive reasoning. We use it constantly, not just in science, but in life. Every prediction, every expectation, every plan relies on it. But Hume pointed out a flaw. Inductive reasoning is not logically guaranteed. You can observe 1,000,000 white swans and still be surprised by a black one. You can eat peanuts 100 times and then have a deadly reaction the next. The past doesn't force the future to obey. It just suggests. And here's the kicker. When we try to justify induction, we usually do it by pointing to the past. Induction has worked before. But that's circular. You're using induction to justify induction. You're assuming the very thing you're trying to prove. Hume said, there is no logical reason the future must resemble the past. We expect it to, but that expectation comes from habit, not reason. Like a dog that hears the food bowl clink and runs to eat, not because it understands physics, but because it's been conditioned. And in a way, humans aren't so different. We expect patterns to hold because we've seen them hold. But that's not the same as knowing they will. This creates a problem for science. Science relies on repeated observation, on testing data and patterns, but all of that rests on the assumption that nature is consistent, that the rules don't just change tomorrow for no reason. Hume wasn't trying to destroy science. He admired it. He just wanted to show that its foundation isn't logic, it's psychology. We believe in patterns because our minds are built to expect them. But the universe never signed a contract promising to play along. That's what makes the problem of induction so unsettling. It doesn't say the future won't be like the past. It just says we can't prove that it will. And that means every expectation, every forecast, every belief that this is how things work is floating, unanchored no matter how solid it feels. Philosophers have tried to respond. Some say, sure, induction can't be proven, but it's still the best tool we have. Others argue that probability theory can patch the gap, that we don't need certainty, just high confidence. And in practice, that works. But the original crack is still there, and it runs through every part of what we think we know. The problem of induction won't stop you from making breakfast, or trusting the weather, or getting on a plane, but it's a reminder. Sometimes, the things that feel most obvious are built on faith and patterns that we've never truly proven will last. The problem of vagueness. Imagine you have a single grain of sand. That's not a heap. Now add one more grain. Still not a heap. Add another, and another. At what point does it become a heap? 2 grains? 10? 50,000? Where's the cutoff? The truth is there isn't one. That's the problem of vagueness. It shows up in words we use every day. Tall, rich, old, bald, smart, warm. All of them are vague. They don't have clear fixed boundaries. If you're 5'11", are you tall? What about 6'1" or 6'4"? At what exact point does tall begin? The problem isn't that we can't use these words. We do it all the time. The problem is, logic breaks down when we pretend they're precise. The classic form of this is the Sorcerer paradox, from the Greek word soros, meaning heap. It goes like this. 1 grain of sand is not a heap. If 1 grain isn't a heap, then 2 grains aren't either. If 2 grains aren't, then 3 grains aren't. Keep going. And by that logic, 1,000,000 grains wouldn't be a heap either. Which is clearly wrong. But where did it go wrong? The logic seems airtight. If 1 grain can't make the difference, then no single grain ever can. But that leads to an absurd result. So either we abandon logic, or we admit that something's off with how we define vague terms, and that's the real problem. Our language runs on fuzzy concepts, but logic wants clean, sharp categories. And when the two collide, strange things happen. Think about legal terms. What counts as reasonable doubt? What counts as cruel and unusual? These aren't just semantic games. They decide lives. Or medical cases. When does someone become legally brain dead? How much function has to be lost before we call it irreversible? There's no perfect line. Just like there's no exact moment when someone becomes old or when a crowd becomes a mob, but decisions still have to be made. So philosophers and linguists have looked for solutions. Some say we need precise thresholds, like anyone over 6 feet is tall. Below that, not tall. That works for some cases, but it feels artificial. What if someone is 5'11.9"? Just barely not tall. It solves the logic problem, but not the human one. Others suggest using fuzzy logic, a system where things can be kind of true. So instead of saying someone is either bald or not, we might say they're 0.8 bald. That preserves the reality of gradual change, but it's harder to reason with. And people don't naturally talk in decimals. Still others say we should accept supervaluationism, a theory that says vague terms can have multiple equally valid interpretations, and a statement is definitely true, only if it's true under all of them. That helps with precision, but it complicates everyday reasoning. And the core issue remains: reality is messy. And the language we use to describe it doesn't always fit into the boxes. Logic gives us the problem of vagueness doesn't mean we stop using words like heap or tall or bold. It means we stay aware that those words don't have exact edges, and that sometimes when we push for sharp lines, we lose the truth in the fuzz. So next time someone says that's not really old or that doesn't count as rich, ask them, where's your line? And what happens if we move it? Just one grain at a time. Next up, the simulation argument. Are we actually living in a computer, say? The simulation argument. Imagine everything around you, this room, your body, your memories, isn't real. Not in the way you think. Imagine it's all running on a computer. The trees, the stars, the air in your lungs, every atom simulated with code. You're not dreaming. You're in a simulation. This isn't science fiction. It's a philosophical argument, and a surprisingly serious one. It's called the simulation argument, and it was introduced by philosopher Nick Bostrom in the early 2000s. Here's how it works. Start with a few basic assumptions. One day, civilizations will be able to run super powerful simulations. They'll have the ability to simulate conscious beings like us. They'll probably run many of these simulations, not just one or two, but millions, billions, for research, for entertainment, for nostalgia. Now think about the math. If advanced civilizations run lots of simulations, then there could be billions of simulated people for every one real person. Which means, if you wake up and find yourself in a world that looks like this, the odds say it's far more likely that you're in one of the simulations than in the one original world that started it all. Bostrom summarizes the logic like this. Either, 1, civilizations never get that advanced. 2, they get advanced but choose not to run simulations. Or 3, they do run simulations, and we're probably in one. The argument doesn't claim to know which is true. It just says, if number 3 happens, even once, then the math becomes overwhelming. The real beings become the rare exception, and the simulated ones, us, maybe become the norm. The simulation argument isn't saying you're in a video game with glitchy graphics. It says, everything you know, physics, history, even your thoughts, could be part of a high-fidelity model running on someone else's hardware. You wouldn't be able to tell, because your perception would be part of the simulation too. This idea has roots going back centuries. Descartes wondered if an evil demon was deceiving us. Others imagined dreams, illusions, minds in vats. The simulation argument just updates the technology. Now the demon is a supercomputer, and the deception, perfect. But what do we do with this? Should we believe it? Should we live differently? Some people take it seriously. Tech billionaires have reportedly funded research to break us out. Others think that's missing the point. Because even if this is a simulation, it's still the only reality we have. Pain still hurts. Love still matters. Ethics don't go away just because we're digital. And if we are simulations, that doesn't make us fake. It just means we exist on a different level than we thought. But not everyone agrees with the argument. Critics say it makes too many assumptions. What if simulating a conscious mind is impossible? What if they're smart enough not to flood the universe with artificial people? Still, the simulation argument holds its power, not because it proves we're fake, but because it forces us to ask, what would be different if we were? And if the answer is nothing, then maybe the line between real and simulated was never as solid as we thought. The lottery paradox. Imagine there's a lottery, 1 million tickets. Only one will win. You pick up a random ticket, ticket 582, 4,000. You look at it and think, this ticket probably won't win. And that's a reasonable belief. The odds are 1 in a million. It's rational to assume it's a loser. Now pick up another ticket. For each individual one, it's totally rational to believe it won't win. But now look at the full set. If you believe every single ticket will lose, then you're also believing no ticket will win the lottery. But that's clearly false. You know one ticket will win. That's the setup for the lottery paradox, introduced by philosopher Henry Keiberg in the 1960s. And it shows something odd. You can believe a bunch of individually reasonable things and still end up with a logically inconsistent belief set. Let's say you have one belief for each ticket. This ticket will not win. Multiply that by 1,000,000. It feels safe, probable, rational. But taken together, those beliefs contradict the known rules of the game. Someone has to win. So now you're stuck. Should you stop believing that any specific ticket will lose? That seems ridiculous. The odds are still tiny. But if you believe them all will lose, you're saying something you know is false. This paradox doesn't just apply to lotteries, it applies to every situation involving probability and belief. Believing every person on a long suspect list is probably innocent, while knowing one of them committed the crime. Believing every journal article might be flawed, while trusting that science still gets it right. Believing every piece of evidence could be wrong, while still making decisions based on the whole. The lottery paradox shows that our beliefs don't always behave nicely when you stack them together. They don't scale smoothly. What's reasonable in isolation can be unreasonable in combination. Philosophers have debated what this means for logic and belief systems. Some say we need to rethink how we treat probabilistic belief. Maybe we shouldn't believe things just because they're highly likely. Others argue that we should limit belief closure, the rule that if you believe A and believe B, you must believe both together. Or maybe we need to say, you can believe something is very likely, but still not fully commit to it as true. That leads into territory like degrees of belief, credences, or Bayesian reasoning, where belief isn't all or nothing, but more like a confidence level. So instead of saying, this ticket will not win, you'd say, I'm 99.9% sure it won't win. That gives you wiggle room, but it also complicates belief. Because now you're tracking confidence, not just truth. The lottery paradox quietly reminds us, logic and probability don't always fit together neatly. And the more beliefs we stack, the more likely we are to trip over the gap between what seems likely and what must be true. Temporal parts and worm theory. Look at your body. It seems whole, complete. You feel like one person, right? But zoom out, not in space, but in time. Look at your life like a film strip. Every frame a different version of you. A baby crying. A kid learning to read. A teenager in awkward clothes. An adult making choices. Maybe one day someone old and fragile. Are all those people really you? Or are they just stages, temporal parts of something bigger? That's the idea behind worm theory. A theory of personal identity that says you're not a single being. You're a four-dimensional worm stretched across time. Just like an object in space has length and width and height, you also have temporal extension. You don't fully exist in any one moment. You exist across moments, and each version of you, today you, yesterday you, 10 years from now you, is just one temporal slice, one part of the worm. This idea challenges the way we think about identity, because we tend to picture the self as a single unified thing, something that moves through time. Yes, but stays the same in some deep way. But worm theory says there is no single you that exists fully at any one point in time. Each moment you're just a part. And the full you, the worm, is the sum total of all your temporal parts. Why does this matter? Because it changes how we think about change, responsibility, and even morality. Think about this. If the person who committed a crime 10 years ago is just one part of the worm, and the person who stands trial today is a different part, is it fair to punish that later slice for what an earlier slice did? What if you don't even remember doing it? Or what about your goals and promises? When you plan something in the future, you're making decisions for a future version of yourself, a different temporal part, with possibly different values. Is that control or manipulation? Worm theory doesn't deny that you're connected across time. It just says the connection is like segments of a train. Each car is different, but together they form one long identity. This idea comes from a broader view in metaphysics called perdurantism, the belief that objects persist through time by having different temporal parts. It's opposed to endurantism, which says things are wholly present at every moment they exist. Worm theory takes perdurantism and applies it to people. And once you do that, some things become easier to explain. How you can have contradictions across time. Young you love soccer, older you hates it. How you survive radical change, yet still seem continuous. How memory connects slices, but doesn't fully unify them. Critics of worm theory say it breaks our intuition. We don't feel like time worms. We feel like whole selves. Right here, right now. But the theory says that's just the illusion of being at one frame in the film. You don't see the whole strip, but it's still you, all of it. Every awkward year, every quiet moment, every future you haven't met yet. You're not a dot moving through time. You're a curve, a stretch, a shape that lives across it. Moral luck. Two people drive home after a party. They've both had too much to drink. They take the same roads, same weather, same level of carelessness. But one makes it home safely. The other hits a pedestrian. One is just a drunk driver. The other becomes a killer. So here's the question. Did they do something morally different, or was it just luck? This is the problem of moral luck, a term made famous by philosopher Thomas Nagel. It points out something uncomfortable. We often judge people not just by what they intended, but by what actually happened, even if that part was out of their control. Take two soldiers in a war. Both follow the same orders. One's attack hits a military base. The other's missile, due to wind, hits a school. One is a hero. The other is labeled a war criminal. Same decision, same reasoning, very different judgment. Why? Because we don't just judge actions, we judge outcomes, and outcomes are often shaped by luck. That's the paradox. If morality is supposed to be about your character, your intentions, your choices, then how can luck play a role? Yet it clearly does. We punish the driver who hits someone more than the one who didn't. We admire the inventor whose gamble worked out, not the one who failed with the same risk. Even in ourselves, we feel more guilt when harm happens, even if we tried to do the right thing. Moral luck comes in different types. Resultant luck, outcomes you couldn't control, like the drunk driving case. Circumstantial luck, the situations you're thrown into. Would you have resisted in Nazi Germany or stayed silent? Constitutive luck, the kind of person you are, your personality, upbringing, impulses. You didn't choose those. Causal luck, the whole chain of cause and effect that leads to any action. If all of that is shaped by luck, what's left for morality to stand on? Some philosophers bite the bullet. They say, yes, we judge people differently because of outcomes. And maybe that's just how human societies work. We need consequences to guide behavior, even if they're not perfectly fair. Others push back. They argue for a stricter form of moral assessment. One that says only intentions matter. If you made the same choice with the same reasoning, you're equally responsible regardless of what happened. But this clashes with our emotions. Our instincts tell us the driver who killed someone did worse than the one who didn't. Even if the difference was just bad luck, moral luck shows the tension between justice and intuition, between the logic of ethics and the emotions of everyday life. It forces us to ask, how much control do we really have? And if so much of what we do and who we are is shaped by chance, how can we take full credit or full blame? The answers aren't easy, but the next time you judge someone harshly or kindly, ask yourself, are you seeing their choices? Or just the way their luck turned out? Frankfurt Cases. Imagine a man named Jones. He's about to make a decision. Maybe he'll vote, or confess something, or take a risk. Unknown to him, someone is watching. A scientist, or maybe a machine. And here's the twist, the observer has the ability to intervene. If Jones starts to choose something wrong, the observer will step in, nudge his brain, trigger a thought, steer him back. But if Jones chooses the right thing all on his own, they won't do anything. They'll just watch. In this case, Jones chooses the right thing. Freely, the observer never needs to act. So here's the question. Did Jones choose freely, or was his freedom an illusion? This is the heart of a Frankfurt case, named after philosopher Harry Frankfurt, who introduced them in the 1960s. And it turns the debate about free will upside down. Most people assume free will means having alternative possibilities. That to choose freely, you must be able to choose otherwise. But Frankfurt said, maybe not, maybe you can act freely, even if you couldn't have done anything else. As long as the choice comes from you, your own reasoning, your own desires, it still counts as free. In Jones's case, the backup plan never activates. He chooses what he was supposed to choose all on his own. So Frankfurt argues the possibility of interference doesn't erase free will unless interference actually happens. This idea challenged a long-standing view in philosophy called the principle of alternate possibilities. That principle says, you are morally responsible for your actions only if you could have done otherwise. But Frankfurt's thought experiment puts pressure on that. What if you couldn't have done otherwise, yet still acted voluntarily? Shouldn't you still be responsible? That's what Frankfurt wanted to show. That moral responsibility isn't about metaphysical escape routes. It's about why you did what you did. If you made the choice because you believed in it, wanted it, endorsed it, then you're responsible, even if behind the scenes there was no real alternative. This is part of a broader view called compatibilism, the idea that free will and determinism can coexist. That even in a world governed by physical laws, where every cause has an effect, people can still be free as long as their actions come from within. Critics push back. They say Frankfurt cases rely on too much fiction, mind control, perfect predictors, improbable setups, and more importantly, they say, even if the interference doesn't happen, its possibility changes the game. Maybe knowing you can't do otherwise, even unknowingly, still undermines your freedom. But supporters argue the opposite. That freedom isn't about branching timelines or metaphysical possibilities. It's about the integrity of your choice, your reasoning, your intention, your inner authorship. Frankfurt cases aren't about robots or trickery. They're about what really matters in moral agency. And they ask, is freedom the presence of options? Or is it the presence of ownership of the choice itself? Because maybe what makes a choice free isn't whether you could have chosen something else, but whether you were the one who chose it. The paradox of choice. You walk into a store to buy toothpaste. You expect 2 or 3 options, but instead there are 27: whitening, enamel care, charcoal, gel, paste, with fluoride. Without fluoride, without fluoride. Suddenly, what should have been a 2-minute decision feels overwhelming. And afterward, even if you pick one, you're not sure you chose the best. You second guess. You wonder what you missed. You feel regret. That's the paradox of choice, a term popularized by psychologist Barry Schwartz. And it flips a basic assumption. That more choice, more freedom, more happiness. It turns out that's not always true. In fact, too much choice can lead to anxiety, decision fatigue, regret, self-blame. When the options pile up, we don't feel more free, we feel more trapped. Why? Because every extra option adds cognitive load. It becomes harder to compare, harder to commit, harder to feel confident, and even if the difference between options is tiny, the cost of choosing grows. This isn't just theory. In one study, people were more likely to browse when offered 24 kinds of jam, but they were more likely to buy when offered only 6. In another, retirement plans with more investment options led to lower enrollment, not higher, because people felt overwhelmed. The paradox of choice plays out in dating apps, streaming menus, course catalogs, even careers. You swipe, scroll, hesitate, and often end up doing nothing. Or doing something, but feeling worse about it. Schwartz distinguishes between 2 types of decision makers, maximizers and satisficers. Maximizers want the best. They search, compare, analyze, worry. They want to make the right choice, objectively, perfectly. Satisficers just want something that's good enough. It meets their needs, and they move on. Guess who tends to be happier? The satisficers, because they're not chasing perfection, they're chasing sufficiency. And that means they live with more peace and less regret. So what do we do with this? Should we limit our own choices? Should society? The goal isn't to ban options. It's to be aware that freedom isn't just about having more. It's also about having clarity, confidence, and direction. A world of infinite menus sounds great, but eventually someone has to order. The paradox of choice reminds us. When every door is open, sometimes the hardest part is just picking one to walk through and not turning around. The Sorcerer's Apprentice Problem. A young apprentice is left alone in the workshop. The sorcerer is out. The apprentice is tired of hauling water by hand. So he casts a spell, animates a broom, and tells it to carry the buckets for him. It works. Water sloshes into the tubs. But soon it keeps going. The buckets don't stop. Water spills, then floods. The apprentice doesn't know how to stop the spell. He tries to break the broom, but it splits in two, and now both halves carry water. The fix has made things worse. This is the Sorcerer's Apprentice Problem, a story made famous in Goethe's 1797 poem and later in Disney's Fantasia, and it's more than a fairy tale. It's a metaphor for automation, unintended consequences, and systems that spiral out of control. Here's the structure. A task is automated or delegated. The system works at first. But something unexpected happens. The creator can't stop it. Every fix makes it worse. Sound familiar? It's in technology. Algorithms optimize for attention, but end up promoting addiction, outrage, and misinformation. You build a system to make things easier, and then it changes behavior faster than you can adapt. Or worse, it adapts around you. You try to correct it, but the fixes interact in strange ways. You're not in control anymore. It's in medicine. Prescribe antibiotics too often. Bacteria evolve. Build stronger drugs. Resistance spreads. The broom keeps multiplying. It's in economics. You stabilize a market, so people take bigger risks. You add regulations. But new loopholes appear. One fix creates the next problem. The Sorcerer's Apprentice Problem reminds us power without understanding is dangerous, especially when the system doesn't pause to wait for feedback, especially when each part starts interacting with the next. What seems like a clever shortcut can become a runaway chain reaction, and by the time you notice, it might be too late to stop it cleanly. Some modern thinkers connect this problem to AI alignment. What if we build systems that optimize goals we barely understand, and they succeed, just not in the way we wanted? The broom fills the room with water. The machine maximizes clicks, not truth. The spell completes the task, but ruins the lab. So what can we do? The apprentice needed one thing: a way to stop the spell. In real systems, that means kill switches, feedback loops, fails, human oversight. But more than anything, it means thinking carefully before you start the spell at all. The problem isn't just lack of control, it's lack of foresight. The apprentice never asked, what happens after it works? In life, in design, in technology, it's not enough to ask, can we automate this? We also have to ask, what happens when the broom doesn't stop? Demandingness Paradox. Imagine you're walking down a road, you take a step forward and see a tall warrior appear in front of you. Just standing there, not attacking, not speaking, but clearly blocking your path. You stop. Then you notice something odd. Behind that warrior, a second one appears, then another and another. For every inch you might move forward, another warrior appears before you get there. You never actually reach them. You never touch them, but you can't go forward. You're trapped. And yet nothing ever physically stopped you. This is Benardetti's paradox, named after philosopher José Benardetti, and it's one of the strangest paradoxes of motion and infinity ever imagined. It works like this. Imagine an infinite sequence of barriers or threats or consequences placed along a line. Each one only appears if you try to pass it. But because there's an infinite number of them, they cover the path, so you never even start moving. Not because anything touched you, but because the potential for interference is infinite. It's a paradox of restraint. You're stopped by things that haven't acted yet, and may never need to. The first warrior doesn't draw his sword, because you never challenge him, but he's there. So are the others. Together they form an invisible wall. A wall made entirely of if you dare. This isn't just a puzzle. It challenges how we think about motion, time, and causation. In physics, we usually think in terms of cause and effect. Something moves, something resists, but in Bernardet's setup, nothing happens, and that's what causes you to stop. Some philosophers connect this to Zeno's paradoxes, like the one where Achilles can never catch the tortoise. Others say it's like a mirror of the Sorcerer paradox. Instead of tiny steps making something appear, infinite tiny threats prevent any step at all. What's strange is that Bernardet's paradox doesn't rely on time. The warriors don't appear one after the other. They're all pre-positioned conceptually there but never activated. You could imagine it with lasers, or trapdoors, or surveillance systems. You never break any beam, you never trip any alarm, but you still never pass. The idea sounds magical, but it raises real questions. Can a series of potential barriers exert real force? Can possibility itself act like a wall? And if we never observe a consequence, but only fear it, can that fear count as a cause? Bernardet's paradox pushes logic to its edge. It forces us to consider infinite structures that act without acting, and it challenges how we define a blockage. Is it the physical impact that stops us? Or is it the reasoning that says, if I try, I'll be stopped, so I won't try at all? In that case, what's doing the work? The warriors? Or your mind? Bernardet didn't solve the paradox, he just laid it out. And let it sit, like a silent army, guarding a path no one ever takes. Pascal's mugging. You're walking down the street when a stranger stops you. They look normal, but they say something very strange. Give me $5, or I'll simulate 10 trillion conscious beings and torture them forever. You laugh. Clearly nonsense. There's no reason to believe them. The odds they're telling the truth are astronomically low, basically zero. But then you think, what if there's a 1 in a billion chance they're right? The cost of ignoring them isn't just $5, it's 10 trillion lives in agony. Even with a microscopic probability, the expected value of that suffering is massive. Mathematically, it might make sense to pay, just in case. Welcome to Pascal's mugging, a modern cousin of Pascal's wager, cooked up by thinkers in probability, ethics, and AI theory. It's called a mugging because it feels like you're being held hostage, not by a threat, but by your own logic. The formula is simple. A very small probability of a very large consequence can still demand a big response. Even if you don't believe the person, the math might push you to act. And that's the problem. Because if you accept this logic, then any wild claim with a big enough threat or reward might deserve attention. Donate to my cult, or 50 universes will explode. Run this code or your descendants will suffer forever. Buy this book or I'll trigger a galaxy-wide plague. Each sounds absurd, but if there's even the tiniest chance they're right, should you do it? That's the dilemma. Expected utility theory says you should weigh outcomes by probability times value, but if the value is large enough, even tiny probabilities can dominate. This breaks our common sense. It opens the door to manipulation. You could be mugged by any theory, cult, or algorithm that claims massive stakes, even if the claim is totally unsupported. Philosophers and rationalists have wrestled with this. One response is to reject the whole framework. Say no if something's too unlikely, ignore it, no matter the stakes. But then you risk ignoring real threats that are rare but catastrophic, like asteroid impacts, or rogue AI, or pandemics. You don't want to be too skeptical. Another option, discount extreme scenarios. Say that we don't have to take into account outcomes that are too far-fetched. But that feels arbitrary. Where's the line? How do you separate ridiculous from low probability but real? Some try to fix it mathematically. They suggest using bounded utility, put a cap on how much value or harm any outcome can have. That prevents huge speculative outcomes from hijacking your decisions. But then you're no longer using pure expected value. You're modifying the rules to make them usable, and that raises a deeper question. If we keep tweaking the math to match our intuitions, are we still doing rational decision theory? Or are we just using math to justify gut feelings? Pascal's mugging may sound like a joke, but it strikes at the heart of how we weigh risk and responsibility, especially in the face of uncertainty. It forces us to ask, what do we owe to future people? How should we act under deep uncertainty? Can we be manipulated by math itself? The takeaway isn't to live in fear of magical threats. It's to be aware of extreme stakes, low probability, fertile ground for confusion. Logic can be a guide, but if you're not careful, it can also be the mugger. The repugnant conclusion. Imagine two worlds. In the first, a small population lives rich, meaningful, joyful lives, deep relationships, art, exploration, beauty, fulfillment. In the second world, there are trillions of people. They're not suffering, but their lives are barely worth living. Minimal pleasure, minimal pain, just enough to say, yeah, I guess this isn't bad. Now, here's the twist. According to one version of utilitarian logic, the second world is better. Why? Because it has more total happiness. Even if each individual has less, the sheer number adds up. This is the repugnant conclusion, a term coined by philosopher Derek Parfit, and it's one of the most disturbing results in modern ethics. It shows how trying to maximize total well-being can lead to wildly unintuitive and uncomfortable results. Let's break it down. The idea starts with something reasonable. If a life is worth living, then adding it to the world makes the world better. That feels right. A happy person is a good thing. But now imagine you can keep adding more lives, each slightly less happy than the last. Eventually, you get a massive population where life is just barely positive, but the total happiness is huge. So by that logic, this overcrowded gray world is better than a smaller, vibrant one, even though no one in it has a life you'd actually want. That's the repugnance. A world full of mediocrity, outweighing a world of excellence. And yet, if you accept the basic math of total utilitarianism, you seem forced into this conclusion. This leads to a major tension in moral theory. Should we aim for total happiness or average happiness? If you switch to average happiness, you avoid the repugnant conclusion. But now you get other paradoxes, like adding a perfectly happy person to a very happy world can actually make it worse because they bring the average down. That doesn't seem right either. Parfit's point wasn't that one answer is obviously correct. It's that any choice leads to strange results. Try to maximize value, and you risk a repugnant future. Try to protect quality, and you might ignore lives worth living. And it gets worse when you apply this to real-world policy. Think about long-term planning, climate change, artificial intelligence, global development. Every decision we make today could affect the size and quality of future generations. If we believe that more lives, thus more good, then we might be compelled to prioritize sheer population growth, even if those lives are marginal. On the other hand, if we value quality too much, we might treat potential lives as if they don't matter. So where's the balance? Some philosophers have tried to escape the repugnant conclusion with person-affecting views. The idea that what matters morally is making life better for people who already exist or will definitely exist, not just for hypothetical future populations. Others try lexical ordering, put higher weight on the best kinds of lives, no matter how many lower ones exist, but no solution is perfect. The repugnant conclusion keeps coming back, not because it feels right, But because on paper it fits the rules we set for ethical reasoning, it forces us to ask, is happiness all that matters? Should we measure ethics with math? Are some lives so marginal they shouldn't count the same? And if so, who decides? The real terror of the repugnant conclusion isn't just the world it describes. It's how easily it follows from ideas we thought were good. It's the feeling that even our best intentions maximize good, reduce harm, can lead somewhere we never meant to go. A future full of lives that no one wants to live. Moore's Paradox. Imagine someone says to you, "It's raining, but I don't believe that it's raining." Or, "I cheated on the test, but I don't believe I did." What do you do with that? The sentence isn't logically false. It's possible in theory that it's raining and someone doesn't believe it, but hearing it said out loud, it feels wrong. Not just strange, but self-defeating. That's the heart of Moore's Paradox, named after philosopher G.E. Moore. It's about a specific kind of statement, one that might be true but can't be said without breaking something deeper. Let's look closely. It's raining. That's a statement about the world. I don't believe it's raining. That's a statement about your belief. Both could be true at the same time. Maybe it's raining and you're just unaware, but the act of saying both together is what causes the paradox. Because when you say it's raining, you're presenting it as something you believe. That's part of what asserting something does. You're not just describing the rain, you're expressing a commitment to its truth. So when you immediately follow that by saying, "I don't believe it," you undercut your own authority. You're asserting something while denying you believe it. That's what makes it paradoxical. Not that it's false, but that it's unassertable. Moore's paradox isn't just a linguistic trick. It's about the relationship between belief and speech. When you say something, you're not just delivering information. You're making a claim. You're putting your belief behind the words. So when your words contradict your own mind, listeners feel the tension. It's not that the sentence is illogical. It's that you can't sincerely say it without sounding broken. This connects to a deeper question in philosophy. What is belief? Is it just a mental state? Or is it something we do, something we express? Moore's paradox suggests belief isn't just what's in your head, it's also what you're willing to say out loud. The paradox shows up in other strange places too. Imagine someone says, "X is true, but I have no reason to believe it." Or, "I'm sure this will happen, but I don't trust my judgment." These aren't impossible, but they feel self-undermining, like the speaker is fighting with themselves mid-sentence. Some philosophers use Moore's paradox to challenge radical skepticism. For example, if you say, "I know I have hands, but I might be a brain in a vat," you're entering Moore territory. You're making a claim that cancels itself out. So what can we learn from all this? Moore's paradox reminds us, saying something involves more than just the words. It's an act of belief, a commitment. And when you try to speak without that commitment, when you separate your mouth from your mind, the logic might still work, but the meaning breaks down. Not all contradictions are in the content. Some live in the speaker. The two envelopes problem. You're given two envelopes. One of them contains twice as much money as the other. You don't know which is which. You pick one. Envelope A. Before opening it, you're offered the chance to switch to envelope B. Should you switch? You think, let's say envelope A has $100. Then B could have $50 or $200. Both are equally likely. So you calculate 50% chance of $50, 50% chance of $200. That's an expected value of 0.5 times $50 plus 0.5 times $200 equals $25 plus $100, which equals $125. That's more than the $100 in your hand. So, you switch. But now you're holding envelope B. You run the logic again. If this has $100, the other must have $50 or $20. Same expected value, $125. So you should switch again. But wait, you just did. and now you want to switch back. The logic says you should always switch, but that leads to absurdity. You just keep switching forever, chasing a better outcome that somehow never arrives. That's the two envelopes problem, a paradox in probability and decision theory. And it shows how a perfectly reasonable calculation can lead to a perfectly irrational loop. So what went wrong? The problem lies in the assumptions you made. When you picked a number, say $100, and assumed the other envelope had $50, you treated both options as equally likely. But they're not. Why? Because the amount in the envelope you picked must have come from a specific distribution, and that distribution matters. Think about it. If the possible amounts were $50 and $100, then picking $100 means the other one must be $50. But if the possible amounts were $100 and $200, then picking $100 means the other one must be $200. Those can't both be equally likely, unless you know how the amounts were generated in the first place. And most versions of the puzzle don't tell you that. They just say, one envelope has twice as much. But without knowing the underlying rules, your expected value calculation floats in midair.
It looks like math.
But it's math built on a missing foundation. Some philosophers say this paradox is a warning about naive expected utility reasoning. Just plugging numbers into an equation isn't enough. You have to understand where the numbers come from. Others say it's about information asymmetry. Once you open an envelope and see a value, you know more and can update your belief. But if you haven't opened either, switching gives you nothing new, and still others argue that the paradox is a trick of self-reference, because the amounts are defined in terms of each other. This one is double that one. You get a loop, not a stable answer, so what should you actually do? If the envelopes are symmetric and you haven't opened either, it doesn't matter. Switching gives you no advantage. If you have opened one, and you know how the amounts were chosen, then you might be able to make an informed guess. But without that knowledge, all you've done is built a castle out of maybes. The two envelopes problem teaches a deeper lesson. Reasoning isn't just about steps, it's about starting points. If your foundation is vague, your logic, no matter how clean, can still lead you in circles.